Good day, I'm Brian Farrell, and welcome to PACE IT's session on Wireless LAN Infrastructure Part 2. Today I'm going to be talking about basic wireless LAN topologies, and then we're going to conclude with wireless LAN concepts and terms. There's a fair amount of ground to cover, so let's go ahead and jump into this session. Of course, I'm going to begin by talking about wireless local area network topologies. And the first topology is the ad hoc topology. It's a very basic wireless local area network that does not require the use of a wireless access point, which can also be called a WAP, and it can also be called an access point. The devices negotiate the wireless connection between themselves. An example of this are when laptops connect wirelessly without the use of a wireless access point. Then there's the infrastructure topology. It's a more common type of wireless local area network that uses a WAP or multiple WAPs to create a connection point for wireless devices. Most often, it's used to connect a wireless network to a more traditional wired network, but that wired network is not absolutely required. Then there's the mesh topology. This is a type of infrastructure topology that employs the use of multiple access points to create larger seamless network coverage areas. They're commonly deployed with wireless controllers and wireless access points. Something to remember is that the higher the wireless device density, the more wireless access points that will be required to handle the load. Like any other network device, access points only have a certain amount of capacity. As the workload increases, the amount of throughput will decrease as each device contends for access to that wireless access point. Adding more WAPs and/or adding more access points and wireless controllers can greatly ease the load and increase the efficiency of the network. Now let's move on to wireless LAN concepts and terms. First up is the IBSS, or Independent Basic Service Set. An IBSS is created when an ad hoc network topology is created. The devices use the IBSS in order to control the communication that occurs between the connected devices. Then there's the BSS, or Basic Service Set. When a single wireless access point is in infrastructure mode, it will create a BSS. This means that it can control the flow of communication between every device that connects to the SSIDs under its control. Then there's the ESS, or Extended Service Set. An ESS is created when two or more access points share a common SSID and have overlapping coverage. Through the Extended Service Set, the WAPs will negotiate how to hand off a wireless device between them as it roams the network. So I mentioned the service set identifier just a moment ago, or the SSID. It plays a key role in the wireless local area network environment. All active wireless access points will use a beacon transmission to advertise the networks that they belong to. What they advertise is their SSID, which can also be thought of as their network name. Those beacons are how devices know which networks they can connect to. Even when an access point is set to hide the beacon, the broadcasts are still occurring. So although hiding the SSID broadcast may make it more difficult to join a wireless network, it's not a true security measure because the broadcast is still occurring. Now let's talk about 802.11a-HT and 802.11g-HT. Both of these terms relate to the 802.11n standard. They denote the type of connection, a high throughput connection, and the radio frequency, which will either be the 2.4 gigahertz radio frequency band or it may be a 5 gigahertz connection. Then there's good put. Good put is the actual amount of application data passed through a connection with the overhead removed. It's measured in bytes per second. It is different than throughput. Throughput measures the total amount of data capable of being passed through a connection, so it includes network overhead. Then we have signal strength. It's a measure of the strength of the radio frequency signal that comes from an access point, which can help to determine the amount of area that can be covered by that access point. As a general rule, the closer a device is to the wireless access point, the stronger the signal that is received. This strength of signal can be affected by wireless access point or antenna placement, the type of antenna used, and interference sources that may be present. A wireless site survey with heat mapping tools can help in the setup of a high-quality wireless local area network, or it can help you to pinpoint problem areas within your network. The heat mapping software builds a visual map by measuring the received signal strength indicator, or RSSI, and the signal-to-noise ratio, or SNR, which can be directly correlated to data throughput. Using these tools allows the administrator to find gaps in coverage as well as areas where the coverage extends beyond the desired boundaries, helping to create a more efficient and secure network. Now that concludes this session on Wireless LAN Infrastructure Part 2. I talked about basic wireless LAN topologies, and we concluded with some wireless LAN concepts and terms. On behalf of PACE IT, thank you for watching this session, and I hope to do another one soon. Good day, I'm Brian Farrell, and welcome to PACE IT's session on risk and security related concepts. Today I'm going to be talking about the big picture of recovery, and then we're going to move on to some concepts and terms that you should know. There's a fair amount of ground to cover, not a whole lot of time, so let's go ahead and jump into this session. We begin with the big picture of recovery. Standards and policies are used to help ensure that everyone is on the same page at the same time. All organizations should review their operations and create standards and policies that suit their needs. Once they are created, the standards and policies should be adhered to. This includes all of the information technology systems. By stressing the importance of standards and policies, risks to an organization can be reduced and security can be strengthened. All policies and standards should be reviewed on a periodic basis to help ensure that they remain relevant and be updated as necessary. One of the standards or policies that should be created is the Disaster Recovery Plan. A disaster is any event or emergency that goes beyond the normal response resources, as in an earthquake or a flood or a major fire. The longer a business is not able to function, the more damage is done. The Damage Recovery Plan, or DRP, detail the steps to recover from a disaster situation, as in when the off-site backups need to be used or if a fallback site needs to be brought into operation. They also have sections dealing with how to help ensure employee safety. A sub-element of the DRP is the Business Continuity Plan, or BCP. A BCP includes an impact analysis of the business effects of down systems. The impact analysis helps to identify single points of failure in the business system. A BCP helps to prioritize what systems or processes need to be brought back first to get an organization operational again. It identifies mission-critical systems, processes, and data. The Business Continuity Plan helps to guide the creation of the Disaster Recovery Plan. Now let's talk about some concepts and terms that you should know. First up is single point of failure. A single point of failure is a system or component that if it goes down has a major impact on operations. An example of a single point of failure is if a key router goes down and it prevents customers from ordering products, that's a single point of failure. Once identified, these failure points can be mitigated through several different methods, such as redundant systems. as in adding a backup router to the previous example, or maybe a redundant power supply. Single points of failure can also be mitigated through system redesign, as in removing that point of failure through a redesign of the system. You should also be familiar with uninterruptible power supplies, or the UPS. A UPS will mitigate power issues that can have a negative impact on sensitive networking components. It conditions the incoming power to remove spikes and sags in the current, helping to ensure that the flow of current is even and consistent, which is very beneficial to your electronic and networking components. They also help to ensure the continued operation, at least for a given period of time, in the case of complete electrical power supply loss, as in an outage. Depending upon your UPS, you may be able to run for minutes, hours, or possibly days if you have a generator. First responders are the first people to discover or respond to a security issue. Ideally, it will be someone who has been properly trained in how to deal with the situation. Within the network security realm, first responders can play a key role in mitigating damage and collecting evidence. Then there's the concept of a data breach, which is any unauthorized access to data, particularly to sensitive data. Breaches may be unintentional or intentional. They may also occur from inside the network, so internally, or they may originate from an external source, so they may come from outside of your network. The severity of the breach is greatly determined by the sensitivity and the quantity of the data that's been accessed. Data breaches can be very expensive to organizations. They can result in a loss of reputation, which can lead to a loss of revenue. When it became known that Target lost sensitive customer information, credit card information, people became unwilling or uncomfortable with shopping at Target. Even though they quickly fixed the breach, the results lingered on. A data breach may result in a loss of business secrets, which may cost that organization a competitive advantage. And finally, data breaches may result in fines or penalties levied by governments or other organizations. User awareness and training can greatly reduce your security risks. Quite often, the weakest link in the security chain is the end user. The risks can be reduced by making the users properly aware of security and security threats through awareness training and just security training in general. This training should be conducted on an ongoing basis. It's never a one and done thing. Penetration testing is the finding of weak spots and the hardening of systems. It is actively and aggressively testing the whole IT system in an effort to find weak spots. This can include using social engineering methods on your end users to find out if they are your weak link. The data generated is used to harden the IT system in an effort to mitigate future risks. Similar to penetration testing is vulnerability scanning. This is the finding of network holes and then plugging them. It's mostly done through the use of automated software. Networks are probed for vulnerabilities, as in open ports or unnecessary protocols. Once these ports or protocols have been identified, these holes into the network can then be plugged. But remember, you need to have authorization to perform vulnerability scanning, or you may be having an uncomfortable discussion with your security personnel. Now that concludes this session on risk and security related concepts. I talked about the big picture of recovery, and then I covered some concepts and terms that you should know. On behalf of PACE IT, thank you for watching this session, and I hope to do another one soon. Hello, I'm Brian Farrell, and welcome to PACE IT's session on common network vulnerabilities. Today we're going to be discussing vulnerabilities associated with unsecure protocols, and we're going to conclude with vulnerable network practices. There's a fair amount of ground to cover, so let's jump into this session. I will begin by discussing vulnerabilities associated with unsecure protocols. Network security is never a completely done deal. It often seems as if as soon as one hole is plugged, another one opens up. Vulnerabilities are discovered all the time, making it difficult for network administrators to keep up. While this is true, there are still some steps that administrators should take to reduce the vulnerabilities that exist in the systems under their control. By reducing known vulnerabilities, administrators can then spend their time preparing for and reducing exposure to up-and-coming threats, thus increasing their productivity. The first vulnerable protocol that we're going to discuss is Telnet. Telnet is a protocol that is used to create a virtual terminal connection that is commonly used for troubleshooting. Telnet is very unsecure because all communication occurs in clear text. Telnet does not support encryption. Whenever possible, Secure Shell or SSH should be used to create those virtual terminal connections in place of Telnet. Then there is SNMP, Simple Network Management Protocol, versions 1 and 2. SNMP is a protocol that is used to remotely manage and configure network devices. Due to their lack of encryption support, versions 1 and 2 are unsecure and susceptible to packet sniffers. This can allow an attacker to grab those packets and actually gain control of the configuration and management of your network devices. If you're going to use SNMP, version 3 should always be used as it supports more security, including encryption. FTP, or File Transfer Protocol, is a protocol that is used to transfer files across a network connection. While a username and password are required in most cases to use FTP, it doesn't support encryption, which creates a vulnerability in the process. Because of this lack of encryption support, everything is done in the clear, making it susceptible to being captured, and you could lose sensitive information. Secure FTP, or SFTP, should be used in place of FTP as it creates an SSH FTP session. TFTP, or Trivial File Transfer Protocol, is a simple stripped-down version of FTP that doesn't support authentication like standard FTP, so it's even more unsecure. It is commonly used to download and upload configuration files for networking equipment. TFTP should only be used when a connection to networking equipment is made through the console port, thus eliminating the possibility of eavesdropping. And that console port should have its own security measures in place. Everyone's fairly familiar with HTTP, or Hypertext Transfer Protocol. It's the protocol that is used to send and receive data over the internet. It is unsecure in its basic format and susceptible to being intercepted due to its lack of encryption. HTTPS, or HTTP Secure, should be used when conducting sensitive business over the internet, as it will provide encryption and other security services. Hopefully your network still doesn't use Serial Line IP, or SLIP. It is an early protocol that was developed for communicating over serial ports and modem connections that required a static IP address. It is very outdated and very unsecure. SLIP does not support encryption. Hopefully you will be using point-to-point protocol in its place. PPP does support encryption and is much more secure. Now it's time to talk about vulnerable network practices. First up are unpatched or legacy systems. Unpatched systems are by their very nature unsecure. Keeping all operating systems and applications up to date will reduce vulnerabilities in the network, and it helps to harden that network against attack. In some situations, it is necessary to keep legacy systems alive. This can create vulnerabilities in the system, as weaknesses in these legacy systems tend to be well known. Special security measures should be taken with legacy systems in order to reduce the opportunity for exploitation. One of the best security steps that you can take is placing these legacy applications or systems on their own network or on their own virtual local area networks. Then there are open ports, and an open port can either be physical or it can be an application port. These open ports create a hole in the security of the network and may be exploited. While not all open ports can or should be closed, security should be placed on these ports that need to remain open to reduce the vulnerability of the network. A good practice is to use a port scanner periodically to verify that only absolutely required application ports are open. Another thing to remember is that you should only use a port scanner if you are authorized to scan that network, or you may end up in a rather lengthy discussion with your security personnel. Unnecessary running services are another vulnerable network practice. Operating system services are used to perform some functions within the system, but it is possible for them to be exploited. A periodic review of all running services should be conducted on all equipment that is attached to the network. All unnecessary running services should be disabled to harden your network. Clear text credentials are another vulnerability that's rather common. Many applications and devices require the use of credentials in order to be used. In some cases, these credentials are sent in clear text format, which makes them easier to read when captured. A good practice is to periodically review all applications and systems to determine which ones use clear text credentials. Then you need to either limit their use or figure out how to encrypt the transmissions to secure your systems. Unencrypted communication channels are another problem. Any method of communication on the network that is not encrypted is an unencrypted channel that is subject to being breached. While not all communication channels need to be encrypted, a good practice is to review all channels and make a decision about which ones need to be encrypted and which ones do not. All wireless network channels should be encrypted. There are no exceptions. Do not create an unencrypted wireless network. That's just asking for problems. A vulnerability that few network administrators think about are RF or radio frequency emanations. One method of intercepting communication is to analyze signal leakage. That's the RF emanation. Many forms of communication are subject to these signal emanations, but there are steps that can be taken to reduce them. Tempest is a set of standards established by the NSA and NATO that outline steps that can be used to reduce the opportunity for the interception and analysis of communication. That concludes this session on common network vulnerabilities. I began with vulnerabilities associated with unsecure protocols. I then concluded with vulnerable network practices. On behalf of PACE IT, thank you for watching this session, and I look forward to doing another one. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Common Network Threats Part 1. Today we're going to be discussing inside jobs or threats, and we're going to conclude with some outside threats to your network. With that, let's go ahead and begin this session. Of course, I'm going to begin by talking about inside jobs or threats. First up is malicious employees. We may not know the reason why they're malicious, but they are difficult to defend against as they are already inside the defenses of the network. And because their employees, resources have been granted to them in order for them to be able to do their job. One of the best defenses against malicious employees is using the principle of least privilege, only granting the least amount of authorization that is required for a person to get their work done. That's the best defense against a malicious employee. Compromised systems are another threat. Once a PC or network device has been compromised, it is vitally important to isolate it from the system as a whole. A compromised PC could lead to a completely compromised network, as malware may be able to spread across its connections. Once malware has gained access to network resources, it can be extremely difficult to root out and remove. Malware may also degrade the network's performance, causing other issues. Then there is social engineering. This is the process of using social pressure to cause somebody to compromise a system from inside the defenses of the network. Social engineering pressure can be applied in multiple forms. An employee can receive a phone call from somebody claiming to be from the IT department asking for their credentials. It may occur in person. The social engineering can occur through email or through a rogue website. There are many avenues in which social engineering can occur. The best defense is through end user education. Training your end users to resist social engineering is a good idea. ARP cache poisoning is another threat that can occur on your network. In ARP cache poisoning, the ARP cache, which maps IP addresses to MAC addresses, is corrupted by an attacker, with the end result being that the attacker has control of which IP addresses are associated with MAC addresses. It's commonly used in man-in-the-middle attacks, which I will cover in just a bit. Then there are protocol or packet abuse threats. This is the process of taking a specific protocol and repurposing it to perform a different function. Protocol abuse is commonly used to bypass a router's access control list from inside of a network. An example of this is encapsulating a not allowed protocol within a DNS packet, which is almost always an allowed protocol, in order to get that unallowed protocol out of the network. The man-in-the-middle attack is another threat that you should be aware of. The attacker is not necessarily inside the network per se, but is in between two endpoints that are communicating on a network. In most cases, the man-in-the-middle attack involves disrupting the ARP process between the two endpoints. The attack allows a malicious user to be able to view all network packets that are flowing between the communicating hosts. Often a man-in-the-middle attack is used in an attempt to gain sensitive information like network credentials. Then there's VLAN hopping. This is circumventing the security that is inherent when virtual local area networks are created. Normally, traffic that is tagged for one VLAN is not allowed onto another VLAN without the intervention of a router. VLAN hopping occurs when the attacker adds an additional fake VLAN tag to the network packets. Once the packets get to the switch strips one of the VLAN tags off the packet and then passes it through. Once through the switch, the packet is considered as belonging to the new VLAN, thus bypassing the security that's inherent in VLANs. Now let's move to outside threats. One of the largest threats that face network security personnel is the unknown vulnerability. Network and systems administrators expend vast amounts of time protecting the assets under their control, and they can do a pretty good job of hardening their systems, but it's not a perfect job. The problem lies with zero-day attacks. Zero-day attacks take advantage of either new or recently discovered vulnerabilities, which means that the networks and systems probably haven't been hardened against them yet. The unfortunate reality is that attacks keep changing, and security experts must be willing to adapt in order to keep pace. If they can't adapt, they will fall behind and their networks become vulnerable. Let's talk about the brute force attack. This is using computing power and time to compromise passwords. The attacker uses a program that continually tries different password combinations, often in the form of a special dictionary application, in an effort to crack a password. The best defense against this is to limit the number of times that a user can attempt to log on before they're locked out. Then there's spoofing. This is a category of threats where either the MAC address or the IP address of the attacker has been modified to look like a friendly address in order to bypass network security. A common use in the past was for an attacker to spoof their IP address so that the outside attacker was actually viewed as an inside host. A common defense against this type of spoofing is an ACL rule that doesn't allow an inside IP address to come from outside of your network. Then there's session hijacking. An attacker attempts to take over a communication session after a user has been authenticated. The hijacking can occur through various methods, as in using a packet sniffer to steal a session cookie or installing malware on a user's computer that is activated after the user is authenticated. That concludes this session on Common Network Threats Part 1. I talked about inside jobs or threats, and then I concluded with a brief discussion on some outside threats. Now, on behalf of PACE IT, thank you for watching this session, and I hope you watch another one soon. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Common Network Threats Part 2. Today I'm going to be talking about more outside threats, and then I'm going to be talking about some wireless network threats. I have a fair amount of ground to cover, so let's go ahead and begin this session. Of course, I'm going to begin by talking about outside threats. Because of how they are implemented, it is often difficult to put network security threats into a single category. Many attempts to breach a network combine different aspects of different threats. For example, a man-in-the-middle attack is often combined with some type of spoofing that is used to help it succeed. That means that in most cases, security requires more than just a single line of defense. Good administrators recognize this and implement multiple layers of security in order to harden and protect their systems. The first major threat that we're going to talk about is the denial of service threat, or the DOS threat. This covers a very broad category of threats to networks and systems. That's because DOS covers any threat that can potentially keep users or customers from using network resources as designed. A traditional DOS attack attempts to flood a network with enough traffic to bring it down. It's commonly used with a flood of malformed ICMP requests. The host that receives the flood can be so busy dealing with the deluge of data that it cannot respond to legitimate requests. Then there's the permanent DOS attack. It's an attempt to permanently deny a network resource for others. It can be achieved by physically destroying or removing the resource, or it can also be achieved through the use of malware that corrupts or damages the underlying digital system to the point where it cannot be repaired and must be replaced. There are also friendly or unintentional denial of service attacks. An unintended DOS attack can occur when poorly written applications consume more network resources than are available. Another unintentional DOS attack can occur when a network interface controller, or NIC, begins to fail. It's quite common when a NIC is about to fail for it to go offline and come back online repeatedly and rapidly. This consumes network resources, which can cause an unintentional DOS. More destructive than the standard denial of service attack is the distributed denial of service attack, or the DDoS attack. It's a denial of service attack in which more than a single system is involved in sending the attack. A DDoS attack has a higher chance of succeeding due to the increased number of participants. The machines used to send the attack may be voluntary participants, this is called a coordinated attack, or they may be part of a botnet. With the botnet, malware has been installed on the machines and they are no longer under the complete control of their owners. Many distributed denial of service attacks involve botnets where the attacker has actually rented the botnet for the sole purpose of performing the DDoS. The goal of the DDoS is to create a large enough spike in traffic that the target becomes unreachable. In some cases, the target system may need to be rebooted in order for it to come back online. There's the reflective denial of service attack. It's also known as an amplified DOS. The attacker uses some method, usually some form of spoofing, to hide the source of the attack. In a reflective DNS attack, the attacker usually spoofs the intended target's IP address and sends multiple requests to an open DNS server. The DNS server responds by sending traffic back to the targeted system, and the attacker's hope is that the response from the DNS server will overwhelm the targeted system. A cousin to the reflective DNS attack is the reflective NTP attack, or the reflective network time protocol attack. It works in the same way. However, instead of using DNS, it relies upon open NTP servers. Not very common anymore, but you still need to know about it, are the Smurf attacks, also known as smurfing. It's a type of reflective denial of service attack that also involves spoofing the intended target's IP address. A network is flooded with ICMP requests in which the source address for the requests appear to be that of the intended target. As the replies return, the network becomes slowed down by the traffic. The goal is to overwhelm the target system and bring it down. It's time to move on to wireless network threats. Our first topic is an unintended threat. A common feature on modern wireless access points is Wi-Fi Protected Setup, or WPS. The goal of WPS is to create an easy and secure method for consumers and small businesses to set up a secure wireless network. Unfortunately, the outcome has fallen short of the goal. While WPS does ease the setup burden, it is also easily exploited by an attacker and should actually be disabled on all equipment. This exploit has been known for a couple of years, and you would think that equipment manufacturers would quit enabling WPS by default on their equipment, but that's not the case. So when you set it up, Good day, I'm Brian Farrell, and welcome to PACE IT's session on Network Hardening Techniques, Part 1. Today I'm going to discuss using secure protocols, using anti-malware software, and I'm going to conclude with implementing switch and router security. There's a whole lot of information to impart, not a whole lot of time, so let's go ahead and begin this session. Of course, I'm going to begin by talking about using secure protocols. Network security is always an ongoing process because the threats to it keep changing. Although security threats are continually evolving, administrators can use some techniques to harden the base network structure to help ease the ever-shifting security landscape. These hardening techniques establish a good security foundation that can be further built upon, making the network that much harder to crack. One of these hardening techniques is to use secure protocols whenever possible. So let's discuss some of those protocols. First up is Secure Shell, or SSH. It's a protocol that is used to create an encrypted communications session between devices. It's commonly used to create a secure virtual terminal session. It should be used in place of Telnet whenever possible. Then there's SNMP version 3. That's Simple Network Management Protocol version 3. It's a protocol that's used to manage and configure devices remotely on the network. It's more secure than the prior two versions because it supports encryption. Secure File Transfer Protocol, or SFTP, should always be used in place of FTP. It's a protocol that's used to transfer data and manage file structures in a secure manner through the use of an SSH session. As I said just a moment ago, it is a better option than FTP, which requires user authentication but does not encrypt the communication. SFTP encrypts the whole process. Then there's TLS, or Transport Layer Security. It's a cryptographic protocol that's used to encrypt online communications. It uses certificates and asymmetrical cryptography to authenticate hosts and exchange security keys. It is a better option than SSL, or Secure Socket Layer, which functions in a similar manner. When performing sensitive online business, you should use HTTPS, Hypertext Transfer Protocol Secure. It's a protocol that is used to secure the communications channel between a web browser and a web server. HTTPS uses either TLS or SSL technology. IPsec, or IPsec, is a network layer IP security protocol suite that can use multiple methods to mutually authenticate both ends of the communication channel. It also will encrypt all data transmissions. Unlike most other protocols, it can provide end-to-end security for any application. Let's move to using anti-malware software. Anti-malware applications help to protect networks and network resources against malware intrusions, as in spyware, viruses, and worms. There are three main options for using anti-malware applications. There's host-based anti-malware. The application is installed on the individual machines and only protects those nodes on which it resides. It's easily tuned to the needs of the individual host, but requires that the user keep it up to date. Then there's network-based anti-malware. The application is installed within the local network and served to the individual clients that require it. It is easily administered, but harder to tune for the individual hosts. But the network administrator can ensure that it remains up to date. And finally, there's cloud-based anti-malware. The application resides in the cloud, so it is outside of the local network. And it is served to the clients inside the local network as needed. This service has a very small footprint on the local machine and tends to be kept more current than the other options. But it is an added cost that must be evaluated. Let's conclude with talking about implementing switch and router security. When is using a password not secure? Well, the answer is when the password is kept in clear text. One solution to this is to save passwords and other sensitive information as hashes. Hashing is a cryptographic process that uses an algorithm to derive a set value, also known as the hashed value, from the sensitive data. The hash can be used to verify that data is coming from where it is supposed to and that it has not been intercepted or changed in transit. The most popular hashing algorithms are MD5 and SHA, or SHA. Of the two, SHA is the more secure. And the wise network administrator makes sure that all passwords and usernames are kept as hashed values. Under implementing switch security measures, switch port security measures are vital. First off, switch port security should be enabled. All enterprise switches are capable of having security measures enabled at the port level, and that should happen. Also, the native VLAN should be changed from its default value. All active ports should be assigned to non-native VLANs. All non-active switch ports should be assigned to an unused non-native VLAN. Also, VLANs should be created to clearly segment the network into logical, secure areas. A switch port security measure that should be considered is MAC address filtering. This will only allow specific MAC addresses to connect to specific ports. DHCP snooping should be enabled. This will only allow DHCP responses from an administrator-defined switch port. This means that all DHCP responses will come from the same port. In addition to DHCP snooping, Dynamic ARP Inspection, or DAI, should also be enabled. This process is combined with DHCP snooping to restrict the opportunity for ARP cache poisoning to occur. All address resolution protocol requests are compared against the ARP table contained in the administratively defined DHCP server. Implementing these measures will greatly increase the security of your switches. Let's move on to router security measures. Each interface on a router should have an access control list, or ACL, in place to control and filter traffic. Each interface can actually have two ACLs. One ACL on the inbound side of the interface and one ACL on the outbound side of the interface. An ACL is a set of rules that is used to govern and filter the flow of network traffic into and out of a network. The ACL examines packets against its established rules, beginning from the first rule at the top of the list and continuing down through all the rules. The rules either allow or deny the packet from continuing. Once the packet matches a rule, the rule is enforced and the ACL process is exited. ACL rules can be based on protocols and ports, IP addresses, source addresses, destination addresses, etc. All ACLs end with an implicit deny statement, meaning that if it isn't specifically allowed, then the packet is discarded. The ACL can be time-based, as in day of the week or time of day, and it can fulfill a specific function based on the reason that it is created. As in, an ACL can be used to filter out websites or web content. That concludes this session on Network Hardening Techniques Part 1. I talked about using secure protocols, then we moved on to using anti-malware software, and we concluded with a brief discussion on implementing switch and router security. On behalf of PACE IT, thank you for watching this session, and I hope to do another one soon. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Network Hardening Techniques Part 2. Today we're going to talk about encryption basics, and then we're going to talk about wireless network hardening, and then I'm going to conclude with a brief discussion on security policies. With that, let's go ahead and begin this session. I'm going to begin by talking about encryption basics. Encryption is the process of taking a message and scrambling the data so that it can't be read if it gets intercepted. Encryption relies upon the fact that the receiver of the scrambled data has the proper key that allows it to unscramble the data and put the message back together. The strength of the encryption is usually determined by the strength of the key. The strength of the key is measured in the number of bits that it takes to generate the key. The more bits that it takes, the stronger the key is. There are two basic types of encryption. There's symmetrical encryption, in which both ends of the communication channel use the same key to encrypt and decrypt the message. Pre-shared key, or PSK, is symmetrical in nature. Then there's asymmetrical encryption, in which two different security keys are used in an arrangement called PKI, or Public Key Infrastructure. The private key encrypts the message and the public key decrypts the message. On the return side, the original receiver encrypts with the original sender's public key, which then gets decrypted with the private key. In this arrangement, the private key cannot decrypt what it encrypted, and the public key cannot decrypt what it encrypted. So it only works if there are two separate keys. So let's talk about those asymmetrical encryption keys. There are two main types of asymmetrical encryption keys. There is the EAP TLS type key, that's Extensible Authentication Protocol Transport Layer Security type of key. It requires the use of a certificate authority, or CA, that is trusted by both parties. The CA provides the certificates to both parties that allow for the generation of both the public and private security keys. It's very secure, but it is also difficult to manage and maintain. Then there's TTLS, Tunneling Transport Layer Security. It's as secure as the EAP TLS, but only the authentication server receives a certificate for the key generation process, and it's easier to manage and maintain than EAP TLS. With that covered, let's move on to wireless network hardening. Wireless networks can represent a special challenge in the network hardening process. The goal of most hardening techniques is to keep nefarious elements from ever seeing the network traffic. But with wireless networks, that is all but impossible, as traffic is broadcast over known radio frequency channels. This traffic is subject to capture, and the transmissions inform any who care that an active wireless network is present. There are steps that can be taken, as in encrypting the traffic, to make sure that even if the network traffic is captured, it cannot be read. This helps to keep the network traffic safe and the network from being breached. One of the first techniques that you can use to harden a wireless network is MAC address filtering. MAC address filtering can be used to limit which devices can connect to the wireless network. If an unknown MAC address attempts to connect to the network, it is ignored by the wireless access point. So when it requests to join, the WAP checks its MAC filter, and if that MAC isn't in the filter, it just drops that requester. While MAC filtering can be effective, it can also be difficult to manage, and it is also possible to spoof MAC addresses. Which brings us to basic authentication and encryption for wireless networks. First up is WEP, or Wired Equivalent Privacy. It's an encryption standard that uses either a 40-bit or a 128-bit encryption key and the RC4 algorithm to authenticate devices and encrypt transmissions. It uses a pre-shared key as a password or passphrase to authenticate users. WEP is easily cracked and should not be used. As a matter of fact, WEP can be cracked in minutes. Better than WEP is WPA, Wi-Fi Protected Access. It's an authentication and encryption standard that improved upon WEP, but still uses PSK and the RC4 algorithm. But to increase security, it also introduced Temporal Key Integrity Protocol, or TKIP. TKIP generates a new security key for every packet, and that new security key has a strength of 128 bits or greater. Now, it's not as easily cracked as WEP, but it can still be cracked and should not be used unless absolutely necessary. And hopefully that's not the case in your wireless network. Better than WPA is WPA2 Personal, Wi-Fi Protected Access 2 Personal. It's an authentication and encryption standard that improved upon WPA. It does not rely upon the weak RC4 encryption algorithm, but it does use AES as its algorithm. That's Advanced Encryption Standard. It can also use the PSK method, but this is not required, as WPA2 Personal can also dynamically assign security keys. While it's theoretically possible to crack WPA2 Personal, it would be extremely difficult to do so, so this should be the minimum level of security on any wireless network. Better yet, if possible, deploy WPA2 Enterprise. Now this forms a portion of the 802.1x standard. It is used to authenticate users on a wireless network and uses one of the forms of the extensible authentication protocol in setting up the encryption. A central authentication server is required for 802.1x or WPA2 Enterprise, which does allow for greater control over the authentication process. As a side note, EAP is actually a set of definitions for how security keys will be exchanged in order for encryption to take place. It's time to conclude with a brief discussion on security policies. While security policies are only written documents, they can actually do quite a bit to harden a network against a breach. Security policies document or outline what is allowed or not allowed to occur on the network from a security point of view. They're usually crafted at the upper layer of management with the help of knowledgeable IT personnel. They establish the expected behavior, which can go a long ways towards hardening your network. Security policies give administrators the authority to put into place measures to protect the security of the network. In many cases, they also give administrators the authority to enforce the policies that lead to a hardened network. Well, that concludes this session on Network Hardening Techniques Part 2. I began by talking about encryption basics, then we moved on to wireless network hardening, and we concluded with a brief discussion on security policies. On behalf of PACE IT, thank you for watching this session, and I hope to do another one soon. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Network Hardening Techniques Part 3. Today I'm going to discuss user authentication, and then I'm going to talk about some authentication and authorization methods. There's a fair amount of ground to cover, so let's go ahead and dive into this session. Of course, I'm going to start by talking about user authentication. Hardening the network will not do you any good if there is poor authentication of the users and devices that are allowed on the network. The process of proving that you are who you say you are, if you are a person, or that you are what you say you are, if it's a device, is called authentication. Authentication is different than authorization. Authorization is what you are allowed to do after you have been authenticated. There are several different ways in which users can be authenticated, and there are several different methods in which authentication can be implemented. Let's talk about basic authentication of the user. There are three basic factors for authenticating users. There's by what you know. This is the user and password method. By what you are. This is commonly implemented through biometrics. And finally, there is by what you have. This is commonly implemented through the use of security tokens. These are the three basic factors for authenticating users. Now you can combine these in a process that's called multi-factor authentication. That's requiring the use of more than one of the factors of authentication, as in requiring a password and a fingerprint scan, or the code from a security token and a password. Those are multi-factor authentication. Now, multi-factor authentication is used to increase the security of the authentication process. You might also implement a single sign-on process. It's a process in which the user only has to provide authentication once via a single smart device rather than having to authenticate for each and every network resource that they request. So let's talk about authentication and authorization methods. The first method we're going to talk about is PAP, Password Authentication Protocol. When logging into a network resource, the user or device is required to supply a username and password. The username and password are sent in clear text format, so this method is considered unsecure and should only be used as a last resort. More secure than PAP is CHAP, Challenge Handshake Authentication Protocol. It is similar to PAP in that when logging into a network resource, the user or device is challenged to supply a username and secret password, and it authenticates through a three-way handshake process. The way it works, the resource issues a challenge. It wants to know the hashed value of the username and secret password. The user's device sends the hashed value to the resource device. The resource evaluates the hashed value and either accepts or rejects the connection. By using CHAP, the username and password are never sent in clear text. It's much more secure than PAP. There's also MS-CHAP. It's functionally the same as Challenge Handshake Authentication Protocol, but it is Microsoft's proprietary implementation of it. You might also implement one of the forms of Extensible Authentication Protocol, or EAP. It's not a single protocol on its own, but a set of additional authentication methods used by remote access clients. Currently, there are more than 100 different methods defined by the EAP specifications. One of the more popular is Kerberos. So let's talk about Kerberos. It's an authentication protocol which uses TCP or UDP port 88 by default. It's a system of authentication and authorization that works well in environments that have a lot of clients. The main component of Kerberos is the Key Distribution Center, or the KDC. The KDC has two parts, the Authentication Server, or AS, and the Ticket Granting Service, or TGS. Here's how it works. When a user logs in, a hashed value of his or her username and password is sent to the authentication server. If the AS likes the hash, it responds with a ticket granting ticket and a timestamp. So it will respond with a TGT that also has a timestamp. The client then sends the TGT with the timestamp to the ticket granting service, the TGS. The TGS then responds with a service ticket, which can also be called an access token or just a token. The service ticket authorizes the user to access specific resources on that network. As long as the TGT is still valid, the TGS will grant additional authorization by issuing a new service ticket as required for as long as the TGT and its timestamp are still valid. Now that concludes this session on Network Hardening Techniques Part 3. I talked about user authentication, and then we concluded by talking about authentication and authorization methods. On behalf of PACE IT, thank you for watching this session, and I trust I'll do another one soon. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Physical Network Security Control. Today we're going to be discussing the why of physical network security, and then we're going to move on to some physical network security practices. There's a fair amount of information to impart, so let's go ahead and begin this session. Of course, I'm going to begin by discussing the why of physical network security. Your network security actually begins at the door. The boundaries of your building should be your first line of defense. If an attacker has physical access to the network resources, then there is a high probability that those network resources can be breached. The level of security that gets deployed should be driven by the amount of security that is needed. As the need for overall security increases, so should the level of physical security. There are dangers that are associated with unauthorized physical access. There is theft of those network resources, and they are expensive to replace. Unintentional damage can occur when there is unauthorized physical access. It only takes a simple spilled drink to destroy a server or a router or a switch or some other expensive component. It's also possible that if an attacker has physical access, they can reconfigure those network resources. This can result in a breached network. One type of reconfiguration that's possible are devices that have credential workarounds. Some networking equipment comes with known workarounds for when administrator credentials need to be recovered. as in when an administrator leaves an organization without disclosing his or her logon credentials, or when an administrator forgets those credentials. Cisco even publishes the steps of its workaround on its website, and those steps are available for anybody to review. If you're curious about those steps, you can check out that web link that I've posted here. This well-known vulnerability is an easy exploit for anybody that has physical access to Cisco equipment. With the why of physical network security out of the way, let's move on to physical network security practices. Basic physical security should include knowing who's in the building and who has access to equipment. You can do that through employee badges. Security check-in should be implemented for all visitors. All vulnerable network resources, as in servers and networking equipment, should be kept in a secure area. Then there's intermediate physical security. This is where access to all vulnerable network resources is controlled and logged. One way to implement this is to use RFID badges to gain access to network resources. Or you could implement cipher locks that people have to punch in a code in order to unlock the door. Another step in intermediate physical security is the separation of resources. Switches and routers are secured separately from servers, with different access levels for the servers and the networking equipment. In environments where high security is needed, advanced physical security needs to be implemented. A zoned approach is an advanced physical security practice. It's a layering of security in which multiple barriers, or security tests, must be passed before physical access is granted. The methods of physical security that are used can be thought of as those security tests. You can use security guards, requiring all authorized personnel to have some form of ID so that the security guards can identify if that person is in an area in which they're allowed. Then there are door locks. You could use simple keyed locks, the analog approach. A slightly more advanced method would be cipher locks, with the deployment of different codes for different areas or different groups of people. This allows for the logging of who has unlocked a door. You might also implement RFID magnetic locks, which also allow for the logging of who has unlocked the lock. One of the most advanced types of door locks would be a biometric lock. They're locks that make the person gaining access prove who they are through either a fingerprint scan or a retinal scan, or possibly even a voice print. Video monitoring can also be deployed as a form of physical security, allowing you to record who has had access to those resources. You need to remember to store the recordings separately from the resources being monitored, so if the resource gets stolen, they don't steal the recording as well. You may implement a separation of resources. Networking equipment is kept separate from servers, and the methods of access for the two resources are different. And finally, in highly secure environments, a man trap may be implemented. A man trap usually involves at least two doors. Access is granted through one door, but the next door cannot be opened until further verification has been achieved, and the person that's between the doors cannot go back out the other door. That means that ideally the person between the doors is trapped until some action or verification takes place. That concludes this session on physical network security control. We talked about the why of physical network security, and then we concluded with a brief discussion on physical network security practices. On behalf of PACE IT, thank you for watching this session, and I hope to do another one soon. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Firewall Basics. Today I'm going to discuss types of firewalls, and then we're going to move on to firewall settings and techniques. I have a whole plethora of information to impart, Not a whole lot of time, so let's go ahead and jump into today's session. Of course, I'm going to start with types of firewalls. First up are host-based firewalls. These are installed at the node, which is usually a desktop computer. They're often used in conjunction with network-based firewalls. Now, host-based firewalls are always software applications. Then there are network-based firewalls. Usually these are implemented on the perimeter of the network segment that needs the protection. They're used to protect private networks from public or outside networks. Network-based firewalls can be a network appliance, which means that it was specially designed and deployed to provide only firewall services, or it can be a software application, either as part of the router's operating system or as a specialty application on a server that is providing some routing function. It's time to move on to small office, home office firewalls. In most cases, the network firewall is provided by a wide area network connection device. So most often the main firewall is provided by the DSL modem or the cable modem. In conjunction with this, a host-based firewall is often used with the network-based firewall. This provides a little bit more protection and it allows for more granular configuration of the firewall protection part of network security. There are stateless inspection firewalls. These examine all the packets either entering or leaving the network. It examines these packets against a set of rules. This set of rules is called an access control list, or ACL. The ACL rules are defined as static values by an administrator. As I stated, all of the packets are examined against the rules in the ACL, starting with the first rule. If a packet matches a rule, that rule is enforced and then the ACL is exited. Stateless inspection firewalls do not care about the state of the connection. They only care about the packets, and all packets are examined. Then there are stateful inspection firewalls. A stateful inspection firewall doesn't really care about the packets, it only cares about the state of a connection between two endpoints. As a general rule, connections are not allowed to be made from outside of the local network segment to the local network segment being protected. Only the initial packets going from inside the network to a destination outside of the network are inspected against an ACL. If the ACL allows those packets to leave the network and a connection is made, or once the connection has been established, the firewall only monitors the state of that connection. It allows the free flow of packets between the inside node and the outside destination as long as the state of the connection remains valid. There are application-aware firewalls. These are firewalls that not only examine the packets, but also the application protocol that is being used. So it knows if it's FTP or HTTP that's being used. Application-aware firewalls make allow or deny decisions based on the application layer protocol as well as other ACL rules. They are slower but more thorough in protecting the private network than firewalls that are not application aware. There are also context-aware firewalls. These are firewalls that can identify not only applications but also users and/or devices. This is the context of the traffic. So context-aware firewalls can be used to restrict or allow traffic based on the context as well as other ACL rules. Then there are Unified Threat Management Devices, or UTM devices. These are network appliances that include not only a firewall service, but other services as well, usually intrusion detection services or intrusion prevention services. One concern with a UTM device is that it can create a single point of failure in the network. What happens to the network if that UTM device fails? Is your security gone, or does the network go down? That is a concern about using a UTM. Most often, firewalls are implemented on a router's interface or at the host level. When implemented on the router interface, the firewall takes part in the routing process. When implemented at the host level, the firewall protects the host on which it resides. There is an exception to these scenarios, and it's the implementation of a virtual wire firewall. This type of firewall is a network-based firewall that resides between two devices and provides neither routing nor switching functions. It contains two interfaces, and as traffic passes between those interfaces, the packets are compared to an ACL. But it's usually not used to protect a specific host, and it does not take part in the routing function. It's time to proceed with firewall settings and techniques. First up is the ACL. Each firewall interface may have two ACLs associated with it, an inbound ACL and an outbound ACL. The inbound ACL examines all packets inbound on that interface. An outbound ACL examines all packets outbound on that interface. The ACL contains a set of administrator-defined rules that either allow or deny packet traffic. Rules can be based on such criteria as source or destination, IP address, MAC address, protocol, and time of day. When an ACL examines packets, those packets are examined against the set of rules from top to bottom. Once a rule is matched, as in deny FTP packets from leaving the network, that rule is enforced and the ACL is exited. The last rule of any ACL is an implicit deny. That means if the packet being evaluated does not match any of the explicit rules of the ACL, the implicit deny is enacted and the packet is blocked. Care and caution should be used whenever creating an ACL, if nothing else because that implicit deny statement ends every ACL list. You may end up blocking traffic that you did not intend to block. It's time to discuss firewall placement, and we're going to begin with perimeter placement. This requires that the firewall be placed at the outside edge, usually at the wide area network connection, of the local segment or the LAN segment. Stateful inspection firewalls work well on the perimeter. They are usually slower to make the initial connection, but once that connection is achieved, they offer better performance. You could have internal placement of your firewall. This requires that the firewall be placed in a logical central location. It's usually used to route between different internal private networks. Stateless inspection firewalls work well for internal placement. They are faster to make connections and require less memory. A DMZ or demilitarized zone requires a special configuration or placement considerations for your firewalls. The DMZ is a specific area that is created, usually between two firewalls, that allows outside access to network resources while the internal network is still protected from outside traffic. You should consider using a DMZ if you're going to have a web server on your network. Outside users will need to access your web server, which is on your network, but your internal network still needs to be protected from malicious traffic. The external facing router allows specific outside traffic into the DMZ, while the internal router prevents that same outside traffic from entering the internal network. That concludes this session on Firewall Basics. I talked about types of firewalls, and then we ended with firewall settings and techniques. On behalf of PACE IT, thank you for watching this session, and I hope to do another one soon. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Network Access Control. Today we're going to be talking about edge versus access control, and then we're going to talk about some access control concepts. With that, let's go ahead and begin this session. Of course, I'm going to begin by talking about edge versus access control. When access to network resources is granted or denied by a firewall, it is considered to be at the edge of the network. So that is edge control. While this may work well in smaller and simpler networks, it can become very complicated and cumbersome as the network grows. Through implementing other access control measures, these complications can be reduced, while at the same time the security of the network may be increased. This idea is called Network Access Control, or NAC. These access control measures do not replace the need for firewalls. They do, however, allow the firewalls to concentrate on controlling network traffic into and out of the network. That is what they do best, and that is what they should be concerned about, not who or what type of device can connect to the network. Firewalls are not very efficient at that aspect of edge access control. Let's move on to some access control concepts. First up is authentication via 802.1x. 802.1x is a popular method of authenticating client devices and users on either Ethernet or wireless networks. When a client device, which is called the supplicant, attempts to join a network, an authenticator, which is usually a switch or wireless access point, requests the supplicant's credentials. The authenticator then forwards the client's credentials to an authentication server, or AS, which is typically running software such as Remote Authentication Dial-In User Service, or RADIUS. The authentication server evaluates the credentials and either informs the authenticator to allow or deny the supplicant device access to the protected network. If the credentials are validated, the authenticator, that's that switch or wireless access point, grants the supplicant access to the protected network. 802.1x is very popular in enterprise-type networks. Access control can also be achieved through posture assessment. This is the process of evaluating more than just the client's credentials. Commonly, posture assessment is used to evaluate the type of device that is requesting a connection. Is it a tablet, or is it a PC, or is it a mobile phone, so on and so forth. Posture assessment can be used to evaluate the type of anti-malware software that's on the device and how updated that software is. During this process, a check is also performed to determine if malware is present on the device. Posture assessment is commonly used to evaluate the operating system as well, as in how updated that operating system is and what the registry settings are at the time that access is being requested. If the client passes the assessment, it is allowed onto the protected network. If the client does not pass the assessment, usually one of two actions are taken. The first action could be that the client is notified of the rejection and what has to occur before it can pass the posture assessment. Does it need an operating system update? Does it need anti-malware installed? So on and so forth. The other action that is commonly taken when a device has failed the posture assessment is that it is passed on to a remediation server, which will then attempt to resolve the cause of the failed posture assessment. It will do this with no user interaction required. Once it has remediated the device and it can pass the assessment, it then goes through the process again and is allowed onto the network if it passes. It's time to move on to the posture assessment process. One of two types of agents, think software code, is used on client devices during the assessment process. It could be a persistent agent, which is permanently loaded on the device and starts when the operating system loads. This type of agent can provide more functionality than the other version. A persistent agent is more likely to be used if that device regularly connects to the network. The other type of agent is a non-persistent agent. When the client device attempts to access the network, the agent is loaded onto the device to help in the assessment process. Once the assessment process is completed, pass or fail, the agent is removed from the device. A non-persistent agent would work best for a guest device. When devices attempt to connect to the protected network, they are placed on a guest network with very limited access. They are left on the guest network until the assessment process is completed. In some cases, particularly when the client fails the anti-malware check, the client device may be placed into a quarantine network, which will only have access to a remediation server, and it cannot move beyond that quarantine network until it can successfully pass the posture assessment. Now that concludes this session on network access control. I talked about edge versus access control, and then we concluded with some access control concepts. On behalf of PACE IT, thank you for watching this session, and I trust you'll watch another one soon. Good day, I'm Brian Farrell, and welcome to PACE IT's session on basic forensic concepts. Today I'm going to be discussing collecting the evidence, and then we're going to have a discussion on what to do after the evidence has been collected. I have a fair amount of ground to cover, so let's go ahead and begin this session. We will begin this session by talking about actually collecting the evidence. The first step in basic forensics is the recognition that forensic measures need to take place, as in that a security incident has occurred. Most of us, at least hopefully, will not need to deal with a murder mystery, at least not in the workplace. With that said, it's almost certain that we will have to deal with some type of security or legal issue when supporting an organization's network. The response to security and legal issues needs to be done in a manner such that evidence is recorded and preserved. The first step is recognizing that something has occurred which needs to be documented and that the evidence needs to be collected and preserved. That's the first step in forensics, at least as far as forensics pertains to network administration. Network administrators and technicians are quite often the first responders to a security breach on IT systems. As such, they have some responsibilities. First off, they need to secure the area and limit who has access as much as possible. Also, do not power down computer systems. The restricting of access and not powering down the systems is done to protect possible evidence from being contaminated. Document everyone who has accessed the area after it has been secured. This protects your chain of custody. If necessary, to stop an ongoing computer attack, it is permissible to unplug the network cable from the computer, but that's it. Once the area is secure, if necessary, now is the time to escalate the response. Depending upon the situation, you may need to bring in specialists or even the police. No matter what, it's important that the scene get documented thoroughly, including what is on any computer monitors. Taking photographs is a great way to document the scene. If photographs are taken, they should be done with a Polaroid type camera and film, not with digital pictures. It's harder to manipulate a Polaroid, and therefore it's more believable than a digital image. It may also be necessary to diagram to draw out the area. Also, interview any witnesses as soon as possible, before their memory starts to degrade or before they begin to collaborate on what story to tell. Also, the electronic evidence collection process needs to begin as soon as possible, and it needs to be collected by order of volatility. So let's talk about the evidence and data collection process. Electronic evidence is volatile and easily corruptible just because of what it is. It's magnetic data. So the order of collection is important. The first thing that should be collected are the contents of memory or RAM. This is the most volatile of all types of data. Next are swap files. They're not as volatile as random access memory, but are still very temporary in nature. Then all network processes need to be documented, at least all of those that are active on the affected system or systems. After documenting network processes, next up are the system processes, and that is all system processes that are active on the affected system. After that, move on to file system information, including the attributes of the files. You need to do this before you do anything else so that you have completely documented the attributes of the files. Once all of that is done, it's time to make a copy of all of the contents on all of the disk drives of the affected systems. And that would be by raw disk blocks. So let's talk about that a little bit more. After isolating the affected system or systems from the network, you need to create a bit level image of the system or systems. That means an exact duplicate of the disk drives. And actually you need to create two copies, two images. And with those two images, you also need to create a message digest of the image drives to be able to later prove that they have not been tampered with. You can use MD5 or SHA as the hash algorithm to make that message digest. One image should be securely stored to be used as evidence, and with that should go the hashed image. That way you can prove in court that it hasn't been tampered with. The other image can be examined and modified in order to determine what exactly happened. Now let's move on to a discussion about what happens after the evidence has been collected. And the first item is the chain of custody. Now this actually starts during the collection period and survives the collection period on into the future. The chain of custody is a document that identifies who collected the evidence, when it was collected, and who has had access to it since it has been collected. Proper chain of custody document can prove that the evidence has been accurately preserved, and the chain of custody document can also be considered part of the evidence. A chain of custody document will help to ensure that all the evidence that is collected is admissible in court. A broken chain of custody will negate the collected evidence. And by that, if your chain of custody gets broken, your evidence is no longer considered evidence. So now let's talk about the e-discovery process, or the electronic discovery process. In legal situations, the discovery process involves the exchange of evidence between both sides of a litigation or prosecution situation. E-discovery refers to the discovery process as it pertains to electronic data, as in email, database files, or chat records, any data that's kept in electronic format. Once identified in the e-discovery process, a legal hold is placed on the data that has been identified. A legal hold occurs when data has been deemed to be possibly relevant in either a prosecution or litigation situation. If a legal hold occurs, all normal processing of that data needs to cease. That data needs to remain in the state that it was in during the e-discovery process. So a legal hold requires that backup tapes not be recycled and that the normal archival process for that data be suspended until the legal hold is removed. There are some items to consider when electronic data needs to be transported and it's considered evidence. If it's physical evidence, as in a hard drive, a chain of custody document must be created for the transportation process, and it needs to include an exact description of the evidence, the means of transport, who received the evidence to transport it, and who had access to the evidence during the transport process. If you're using electronic means of transport, a message digest should also be included to prove that the exact evidence sent is the evidence that is received. Once the forensic process has concluded, or once the investigation has been completed, a forensic report needs to be created based on the findings of the investigation. During the evidence collection and investigation process, the characteristics of the evidence should have been documented, so you know what timestamps were present or any identifying properties that are associated with that evidence. All of this information needs to be recorded and analyzed using scientific methods. Once completed, the forensic report should be able to completely reconstruct and document the evidence. A forensic report may be used in the litigation or prosecution process. In addition, a good forensic report may help in the creation of a better response plan for use in the future. Now that concludes this session on basic forensic concepts. I talked about collecting the evidence, and then we concluded about what happens after the evidence has been collected. On behalf of PACE IT, thank you for watching this session, and I hope to do another one soon. Good day, I'm Brian Farrell, and welcome to PACE IT's session on network troubleshooting methodology. Today I'm going to be talking about the importance of a methodology, and then I'm going to cover the 7-step troubleshooting methodology recommended by CompTIA. There's a fair amount of ground to cover, not a whole lot of time, so let's go ahead and begin this session. We are going to begin by discussing the importance of a methodology. First up is one of my favorite quotes concerning methodologies, and it is, "My methodology is not knowing what I'm doing and making that work for me." That's from Stone Gossard of Pearl Jam, and unfortunately, we don't quite have that kind of liberty when it comes to troubleshooting networks. All networks will require troubleshooting. If you don't know where to start or haven't developed a methodology, you will waste time and resources. The complexity of modern networks means that there is a lot that can go wrong. Without a troubleshooting methodology, your frustration levels and the frustration levels of those you support is going to rise. A systematic troubleshooting methodology can significantly reduce the time required to resolve a problem and close a network trouble ticket, saving both time and other resources. It's time to move on to CompTIA's 7-step troubleshooting methodology. Of course, we're going to begin with step 1, which is identify the problem. Gather information. What is actually occurring or not occurring? Is the problem extremely local, as in relegated to your network? Or is the problem occurring in an area that is out of your control? Identify the symptoms. Remember, the symptoms are not the problem. They just point toward the underlying issue. Most often, when the trouble ticket comes in, it will have some of the symptoms, but it will not have identified the actual problem. Approach multiple problems individually. Handle them one at a time. Question the users. This needs to be done both politely and firmly. Many problems that are reported within a network are the result of the end user needing to be educated or re-educated in proper procedures. At the same time, you also need to remember that most end users don't have your level of technical knowledge. So be patient, but don't patronize. And finally, when identifying the problem, determine if anything has changed. This also requires a systematic approach, so be very thorough. Step 2 is to establish a theory of probable cause. Make a list of all of the possible causes of the problem. To develop this list of possible causes, you should consider multiple approaches to the problem, from bottom to top and then from top to bottom of the OSI model. That is a great way to approach the problem from multiple directions. Divide your list of possible causes into 3 ranked sections. They should be not likely, likely, and most likely. This will provide a great place to start. When establishing your theory of probable cause, remember to question the obvious. If the network printer doesn't work, check to be sure that it is turned on. The third step is to test the theory of probable cause. If the theory is confirmed, move on to the next step. If the theory is proven to be incorrect, then reestablish a new theory of probable cause. If you run out of probable causes or the situation worsens, it may be time to escalate the issue up the troubleshooting chain. Once you've confirmed your theory of probable cause, it's on to step 4. Establish a plan of action and identify potential effects. Simple problems may require a simple plan, as in if the network printer doesn't work and the probable cause is that it's not turned on, turn on the network printer. More complex problems will require more complex plans. In some cases, it is a good idea to write the plan out step by step in order to determine the best course of action and to identify any possible repercussions that the resolution to the problem may introduce into the network. Step 5 is to implement the plan or to escalate the problem. If you have the authority, put your plan into action. If you don't have the authority, escalate the problem up the troubleshooting chain, including all facts and determinations when you're escalating the problem. Don't make that next level above you have to recreate everything that you've done. Once you've implemented your plan, it's on to step 6. Verify full system functionality. Don't just verify that the original problem has gone away, because sometimes a fix will introduce a new issue into the system. If a new issue has occurred, it's time to go back to step 1 or to escalate the problem. If you have verified full system functionality, this is where you implement preventative measures to keep this problem from reoccurring. And finally, step 7. Document findings, actions, and outcomes. Document everything. This will save time if and when the problem reoccurs. Your documentation may lead to new best practices for your organization. It's important to document your missteps as well. It will keep the next technician from making those same missteps that you have made. And this will help to improve your chances of becoming the network support technician rock star in your organization. That concludes this session on network troubleshooting methodology. I talked about the importance of a methodology, and then I covered CompTIA's 7-step troubleshooting methodology. On behalf of PACE IT, thank you for watching this session, and I hope to do another one soon. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Troubleshooting Connectivity with Utilities. Today I'm going to talk about Connectivity Utilities Defined, then I'm going to move on to Connectivity Utilities Explained, and we will conclude with some additional software for troubleshooting connectivity. There's a fair amount of ground to cover. Let's go ahead and begin this session. Of course, I'm going to begin with Connectivity Utilities Defined. Before we can define the utilities, we need to define connectivity. Connectivity is a program or device's ability to connect or link to other programs or devices. A connectivity utility is a utility or application that is used to establish connectivity and or to diagnose or fix a connectivity issue. With that out of the way, let's move on to Connectivity Utilities Explained. All modern operating systems come with pre-packaged connectivity utilities designed to diagnose and or to repair connectivity issues. In some cases, you can use these utilities or programs from a graphical user interface or GUI. However, in all cases, you can use the following applications from the command prompt. First up is ping. It is a simple utility that is used to determine if there's connectivity between two nodes or two endpoints. It uses ICMP echo requests. There are two basic formats to the ping utility. You can ping an IP address, or you can ping the host name or the fully qualified domain name. You can use ping 6 or ping -6, and you will ping only IPv6 hosts. Then there is tracert or traceroute. It is a utility that is used to determine the path used between two nodes. Tracert, T-R-A-C-E-R-T, is the Windows version, and Traceroute, T-R-A-C-E-R-O-U-T-E, is the Linux, Unix, or OS X version of the command. It also uses ICMP echo requests, but it uses it with an incrementing time-to-live field to form queries and get responses. Each time the ICMP echo request is sent out, the TTL field is incremented by 1. And Tracert is used to determine how many routers are between 2 points. It can be of limited value though, as many routers have ICMP disabled. It uses the same basic format as ping. Then there is PathPing. It is a network connectivity utility that has been supplied in Microsoft operating systems since the introduction of NT. PathPing builds upon the functionality of ping by combining it with Tracert. When the application is used, it will, in effect, perform a Tracert command, defining the path to the end node, and then it will perform a ping test on each hop. One disadvantage to PathPing is that it requires 25 seconds per hop to show the ping results, and it uses the same command format as ping and Tracert. One of my favorite utilities is ipconfig or ifconfig. ipconfig is the Windows version and ifconfig is the Linux, Unix, OS X version. It's used to determine the IP configuration of a given node. It can also be used to change that IP configuration if used correctly. When using to diagnose connectivity, look for incorrect IP addresses, incorrect subnet masks, incorrect DNS addresses, and/or an incorrect default gateway. Then there's ARP, which stands for Address Resolution Protocol. ARP is used to correlate IP addresses to MAC address. This utility can help to determine when there is an issue with an address resolution protocol table on a given node. Then we have NSLookup. That stands for Name Server Lookup. It's supported by all major operating systems, and it's used to diagnose domain naming system issues or DNS issues. It can be very helpful in determining if a DNS server is having a problem. DIG is similar to NSLookup, but it is specific to Unix, Linux, and OS X. It does use different switch modifiers and returns slightly different results. There is the route utility. This is a Windows-specific command. It's used to view and modify the routing tables on a Windows operating system node. Next up is NBT stat, which stands for Net BIOS over TCP statistics. Windows implements the NBT protocol for backwards compatibility. As a result, the NBT stat utility is used if a Net BIOS issue is suspected. Then there's NetStat, which stands for Network Statistics. It's a utility that is used to display protocol statistics and current TCP/IP network connections. It's useful for determining if a connection has been made and the status of that connection. It's time to move on to some additional software. First up are throughput testers. They're used to determine the data flow or bandwidth of a network. They can be used internally to test the flow or bandwidth within a local area network, or they can be used externally to test the flow of a WAN connection. They are often used to create a baseline of network performance. And last up, we have protocol analyzers. These are often called packet sniffers. They examine network behavior on a very basic level, at the packet level. They can examine all the packets coming into and out of an interface. Protocol analyzers are useful to see what is consuming network resources, as in they can tell if a broadcast storm is occurring or if an interface is going bad. Wireshark is a common protocol analyzer that is often used, and it's free. That concludes this session on troubleshooting connectivities with utilities. The first topic was connectivity utilities defined, then we moved on to connectivity utilities explained, and we concluded with a brief discussion on some additional software. On behalf of PACE IT, thank you for watching this session, and I hope you watch another one soon. Hello, I'm Brian Farrell, and welcome to PACE IT's session on troubleshooting connectivity with hardware. Today I'm going to discuss what makes a cable bad, cable testing tools, and I'm going to conclude with some additional tools. I have a fair amount of ground to cover, so let's go ahead and begin this session. We will begin with what makes a cable bad. Network cables can go bad or be bad without any visible indication. Alternatively, a cable may be inappropriate for a particular application. It can be difficult to visually tell if cables are wired correctly and/or a break in the wire may not be visible. Both of these will cause problems. Additionally, anything that makes the cable fall out of specification will make it a bad cable. How long is the cable? Is it over the maximum length? Is the cable rated for the amount of data being run over the wire? All of these are questions that can be answered using the proper tools. It's time to discuss cable testing tools. First up is the multimeter. It can be used to test for breaks in copper wiring. Good network cables have a very low resistance value from one end of the cable to the other. By the way, your resistance is measured in ohms. A high or infinite ohms value indicates a break in the cable. So you can use multimeters to test for continuity to make sure that traffic can flow from one end to the other. Crimpers are not a testing tool per se, but they are used for attaching cable ends onto cables, which if you suspect you have a bad cable end or a miswired connector, you're going to need a set of crimpers. It can either be specific to a particular type of cable end, or it may work for more than one type of cable. And by the way, it's not uncommon to need to replace the ends of twisted pair wiring cables. Every network technician should have a cable tester or cable certifier. These can be either fairly simple or very complex. Cable testers will test for continuity in the wire, as in, is there a break? Cable testers will also test for proper pinouts. Are all the wires in the right places? Some will test for the wiring standard. Is it wired for the T568A standard or the T568B standard, or have you created a crossover cable? Cable certifiers are a little bit more complex, but they will also test for more network-related items. They can test the speed of the wire. They can test for duplex settings between two endpoints. Cable certifiers are used to certify a given network segment. Toner probes are another handy tool. They are usually a two-piece set. They have an injector which places a signal onto the wire and a probe which detects the signal and emits a tone when it detects that signal. These are also sometimes called a fox and hound. They're used to find and trace wires. They're useful when having to replace a single wire in a bundle of wires. You can place the injector on one end to figure out which wire it is at the other end. Then there is the time domain reflectometer. This is a cable tester or certifier that can also determine the length of a segment. They can also tell where a break is in a segment, which can then allow you to put in a splice. They are more expensive than a standard cable tester or certifier. Related to the TDR is the optical time domain reflectometer, or the OTDR. They perform the same function as a TDR, but it is used for fiber optic cabling. It is often called a light meter, as it can measure the quantity and quality of the light going through a fiber optic cable. Some other thoughts on cable testing tools. Unless your job entails mostly installing cabling, the most important tools are the cable tester, crimper, and toner probes. Personally, I have never been able to justify the cost of a TDR. I have used them, but I've rented them instead of purchased them. Most of the time, you can make do with inexpensive tools. However, spending more on certain tools will usually save time and money in the long run. An exception to the inexpensive tool rule are toner probes. Inexpensive toner probes can be difficult to work with, or they just don't work at all. I would recommend stepping up and spending a little bit more for your toner probe. Try to strike a balance between cost and effectiveness. You can spend thousands of dollars on some of these tools, especially TDRs and OTDRs, and never utilize them to their fullest potential. The next topic is additional tools. And we will begin with the wireless analyzer. It is a similar tool to the protocol analyzer, but it is used for wireless networks. It sniffs out packets on wireless networks. This information can be used to help solve wireless connectivity issues. A wireless analyzer can also perform other functions. It can check for bandwidth usage, channel usage, top talkers, and top listeners. It can identify networks by passively scanning the radio frequency channels. It can identify hidden networks if given enough time, and a wireless analyzer can also infer non-beaconing networks based on data traffic, so it can help you to find those rogue access points. Then there are looking glass sites, or LG sites. These are publicly available sites that can be used to view routing information remotely, as viewed from the LG server's point of view. They create a read-only portal on which routing statistics can be generated and viewed. LG sites can be helpful in determining if the connectivity issue is occurring because of problems on the local network or if the remote connection is the issue. That concludes this session on troubleshooting connectivity with hardware. I talked about what makes a cable bad, I talked about cable testing tools, and I concluded with some additional tools. On behalf of PACE IT, thank you for watching this session, and I hope to do another one soon. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Troubleshooting Wireless Networks, Part 1. Today I'm going to be talking about configuration issues, and then we will conclude with some other issues. There's a fair amount of information to go over, so let's go ahead and begin this session. I will begin by talking about some common configuration issues. While wireless networks are a huge convenience to users, they do introduce a new set of troubleshooting issues into the network. Not only do the standard issues that crop up in a wired network need to be considered, the added layer of complexity that adding a wireless access point brings to the table will also need to be considered. When wireless networking is brought into the mix, a very solid troubleshooting methodology becomes just that much more critical. Now on to the actual configuration issues. First up is the Service Set Identifier configuration, or the SSID configuration. When this is an issue, the major symptom is that the user is unable to connect to the wireless network, and the probable cause is an SSID mismatch. The corrective measure is to check that the SSIDs match exactly. Remember, they are case sensitive. Then there is encryption configurations. It has the same symptom as the SSID misconfiguration. The user is unable to connect to the wireless network. Probable cause is an encryption type mismatch or incorrect security key. The possible corrective measure is to check the encryption settings on the wireless access point and on the device to make sure they are the same. Another configuration issue that can cause problems is an incorrect channel or overlapping wireless channels. The symptom is that the user is unable to connect or the wireless network has very poor performance. The probable cause is either incorrect channels or the overlapping channels is causing the signal to noise ratio to be reduced. That's the SNR. The possible corrective measure include adjusting the WAP settings and device settings so that they're using the same channel. Hint, there are only 3 available non-overlapping channels on the 2.4 gigahertz radio frequency. Then there are incompatibilities. And the symptom is, again, the user is not able to connect to the wireless network. The probable cause is you have an 802.11a device being used in an environment in which it won't work, as in you're using 802.11g or n. Or there is a frequency mismatch between the wireless access point and the devices. The possible corrective measure is to make sure you're using equipment with compatible wireless standards. Untested updates can also cause a configuration issue. The symptom again is the user is unable to connect or there is poor performance. The probable cause is a conflict between the update and other configuration settings or the wireless network settings. The possible corrective measure is to roll back the system to the prior configuration. Here's another hint. It is a best practice to make a backup copy of a system before installing any updates. Let's move on to other wireless issues. Troubleshooting networks requires a combination of art and science. Some of the best tools in your arsenal will be patience and strategic thinking. Network issues can express themselves in a multitude of ways. One of the best things that you, as a technician, can do is to see if you can recreate the problem. An issue that can be recreated can usually be resolved easily. Also remember that the users you are dealing with are the reason that you have a paycheck. Treat them as you would like to be treated, even if it is the 10th time that you've reminded Bob that his username and password are case sensitive. Interference is a common issue on wireless networks. The symptoms include slow performance and/or intermittent drops. The probable causes can include overlapping channels, walls, or other equipment that operates in the same frequencies. Some possible corrective measures include changing the RF channel or frequency or adjusting the wireless access point placement. Then there's poor signal strength. The symptoms include slow performance and/or intermittent drops, especially towards the end of your wireless network coverage area. Probable causes include low RF power settings, antenna type, and/or the placement of the access point. Possible corrective measures include changing the RF power setting, as in increasing it, or adjusting the antenna and/or WAP placement. There is a caution here. Increasing your radio frequency power or adjusting the equipment placement may cause the signal to go where it was not intended to go. So if you do either of those, you need to check and make sure that you're not putting your signal where you don't want it to be. Bandwidth or device saturation can also become an issue. The symptoms include slow performance and/or intermittent drops. The probable cause is that there are too many users or applications for the available bandwidth. Possible corrective measures include increasing the number of wireless access points and/or changing to a wireless standard with more throughput. The wrong antenna type may also become an issue. The symptoms include low or no signal in an area or signal in an area where it is not supposed to be. The probable cause is the wrong antenna type for the coverage. The corrective measure would be to change to an antenna type to suit the required coverage. Then there is signal bounce. The symptom is poor performance in unexpected locations or an unexpected wireless network signal in an area that was not intended to be covered. The probable cause is the RF signal bouncing off of a hard object. The possible corrective measure would be to adjust the wireless access point placement. That concludes this session on Troubleshooting Wireless Networks Part 1. I talked about configuration issues and then I moved on to some other wireless network issues. On behalf of PACE IT, thank you for watching this session and I hope you watch another one soon. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Troubleshooting Wireless Networks, Part 2. Today I'm going to be discussing wireless environmental factors, and then we're going to conclude with wireless standard-related factors. There's a whole lot of ground to cover, so let's go ahead and begin this session. Of course, I'm going to begin by talking about wireless environmental factors. When planning and setting up a wireless network, quite often environmental factors that may impact the wireless network are disregarded. It is easy to get distracted by all the moving pieces of the wireless network, as in the SSID configuration, encryption, and which standards to use. Dealing with these often leads to overlooking factors in the environment that may impact the quality of the planned network. To get the most out of a wireless network, these factors need to be taken into consideration as they can have a major impact on the overall quality and performance of the installed network. We don't think about it very often, but building materials can influence wireless networks. A wireless network works by sending and receiving radio frequency waves across a given area. Anything that can interrupt the signal or change the path of the waves can create a problem in the network. This is called signal bounce. The signal may return to the wireless access point out of phase, leading to poor performance or dropped packets. Alternatively, the signal may end up being bounced into areas where coverage was not planned, leading to a security issue or an interference issue with other wireless networks. Some building materials of concern include concrete walls, metal studs, and window films, particularly window tinting with a metallic content. When evaluating environmental factors, it is important to consider more than just the building materials. All hard surfaces have the potential to create an out-of-phase or bounced signal, including office furnishings and file cabinets. Using a wireless analyzer and wireless survey tools during the planning stage of a wireless network will lead to better placement of the wireless equipment, which ultimately leads to a better performing network. Let's move on to some wireless standard related factors. First up is wireless standard compatibility. Not all of the 802.11 standards are compatible with each other. This is partially due to the RF frequencies that are used, and with the most common frequencies being the 2.4 GHz or the 5 GHz radio frequency band. The problem with compatibility can also be because of the type of modulation that is employed. Modulation is the encoding of information to be placed on a carrier wave, and it's employed to put the signal on the network. The most common forms of modulation are orthogonal frequency division multiplexing, OFDM, and direct sequence spread spectrum, or DSSS. So let's look at a compatibility list for 802.11. 802.11a is not compatible with most other standards. 802.11b is compatible with 802.11g and n. 802.11g is compatible with .11b and .11n. 802.11n is compatible with 802.11b, g, and AC. 802.11ac is compatible with 802.11n. So let's talk about the wireless standards. 802.11b uses the 2.4 GHz RF band and DSSS as its form of modulation. It offers up to 11 megabits per second networking with a maximum indoor range of 115 feet and a maximum outdoor range of 460 feet. 802.11a uses the 5 GHz RF band and OFDM as its method of modulation. .11a offers up to 54 megabits per second networking with a maximum indoor range of 115 feet and a maximum outdoor range of 390 feet. Then there's 802.11g. It uses the 2.4 gigahertz RF band, and it can use both OFDM and DSSS as its methods of modulation. 802.11g offers up to 54 megabits per second networking with a maximum indoor range of 125 feet and a maximum outdoor range of 460 feet. Then we have 802.11n. It can use both the 2.4 and the 5 gigahertz radio frequency bands with OFDM as its method of modulation. 802.11n can offer up to 600 megabits per second networking with a maximum indoor range of 230 feet and a maximum outdoor range of 820 feet. Finally, we have 802.11ac. It uses the 5 gigahertz radio frequency band with OFDM as its method of modulation. It's expected to offer up to 1 gigabits per second networking with a maximum indoor range of 115 feet. At this point in time, we do not have a maximum outdoor range as they're still working on establishing that. That concludes this session on Troubleshooting Wireless Networks Part 2. We talked about some wireless environmental factors, and then we concluded with a brief discussion on wireless standard-related factors. On behalf of PACE IT, thank you for watching this session, and I hope to do another one soon. Hello, I'm Brian Farrell, and welcome to PACE IT's session on troubleshooting fiber cable networks. Today we're going to be talking about using the specific tool for the job, and then we will conclude with some common fiber cable problems. There's a fair amount of ground to cover, so let's go ahead and begin this session. Of course, I'm going to begin by talking about using the specific tool for the job. The nature of fiber optic networks makes troubleshooting them a little more expensive than other types of networks. The reason for this is that the best, and sometimes only, tool that can be used for troubleshooting fiber optic cable problems is the Optical Time Domain Reflectometer, or the OTDR. Using the specific tool for the job at hand will ease the burden of diagnosing and resolving any network issues. While an OTDR costs thousands of dollars, or in some cases tens of thousands of dollars, in many cases it can quickly diagnose the problem. A quick diagnosis can lead to a quick solution, often saving significantly more than the cost of the tool by preventing lost productivity and/or revenue. That is why we spend money on OTDRs. So let's talk about some common fiber cable problems. We're going to begin by talking about attenuation or decibel loss. All network transmissions degrade over distance. This is called attenuation or decibel loss. This loss of signal strength can lead to slower speeds, loss or corruption of network traffic, or the loss of the network communication link. The OTDR can not only diagnose attenuation, but it can also help in the placement of a repeater station. Then there's broken fiber optic cables. As with all types of cable media, fiber optic cables are subject to breakage. As a matter of fact, in some cases they are more delicate than other types of media. Certain types of fiber cable can span many kilometers, making it difficult to determine where a break has occurred. The OTDR can be used to determine where a break in the fiber optic cable has occurred, allowing the technician to insert a splice at that point. A common cause of breaks in fiber optic cable is exceeding the bend radius limitations of the cable. Due to the construction of fiber optic cables, it is subject to breakage if it is bent beyond a certain point. It is possible for small form factor pluggable transceivers or for gigabit interface converter transceivers to go bad. The SPF and GBIC transceivers are hot swappable, replaceable modules that are used to add gigabit capabilities to switches, routers, and other networking equipment. A bad transceiver will prevent communication from occurring. An OTDR can be used to help diagnose a bad SPF or GBIC module. it is possible to have a fiber type mismatch. Single mode fiber and multi-mode fiber use different methods for placing the signal on the optic fiber. If a mismatch occurs, the most common problem is that it will be impossible to make a network connection. This is also referred to as a wavelength mismatch, as the wavelength or color of the light being used is different between the modes of fiber transceivers. The OTDR can be used to determine the types of transceivers that are being used. There are some other fiber optic cable issues that can arise. Anything that can interrupt the flow of light from transceiver to transceiver will create a problem. Dirt or smudges on the connectors may cause an issue with fiber optic cable transmissions. When this is suspected, using a soft polishing cloth to clean the ends of the cable will solve the problem. There is a caution: never look directly into the ends of connected fiber optic cable. If you do so, you run the risk of damaging your eyes. Connectors are also specific to the mode of transmission, as in SMF or MMF. Connecting the wrong type of connector to a cable will prevent proper communication from occurring. Also check to make sure that the proper connectors are being used with the proper type of fiber optic cables. Worn or broken connectors will create an air gap, which will create a network transmission problem. Always inspect the connectors for their condition before use. An OTDR can be used to determine where the loss of signal is occurring, even if it is at the connector. That concludes this session on troubleshooting fiber cable networks. We talked about using the specific tool for the job, and then we concluded with common fiber cable problems. On behalf of PACE IT, thank you for watching this session, and I hope you do watch another one soon. Good day, I'm Brian Farrell, and welcome to PACE IT's session on troubleshooting common network issues. Today we're going to talk about problems that should be escalated, and then we will conclude with problems that you should resolve. There's a fair amount of ground to cover, so let's go ahead and begin this session. We're going to begin by talking about problems that an entry-level network technician should escalate. The complexity of modern networking has made using a solid troubleshooting methodology a necessity, not an option. Networks can express problems and issues in many ways. This can lead to much frustration on the part of the network users and the technicians responsible for fixing problems. If such problems are not resolved quickly, they can lead to loss of revenue and productivity for an organization. There are a number of problems that should be escalated up the troubleshooting chain as soon as they're discovered in order for them to be resolved in the most expedient manner. The first of those problems is the switching loop. Users complain that the network works fine for a while and then goes down, and then works fine for a while and then goes down. This indicates a spanning tree protocol convergence issue or a switching loop. In either case, this is beyond the entry-level technician's capabilities and should be escalated as soon as possible. Then there's the broadcast storm. A failing NIC or application may cause a situation in which a broadcast storm is created. The NIC goes down, then comes back up, then goes back down, and it does this repeatedly. This is often referred to as a flapping NIC. Each time it comes up, it sends out a broadcast advertising its status, which creates traffic congestion. An application can do the same thing. In either case, escalate this up your support chain as soon as it's discovered. Similar to the switching loop is the routing loop, but it involves the routing process. This is more likely to occur when older routing protocols are used, but may also occur due to a misconfiguration of routers, as in there are multiple static routes to the same location. Often switching to a newer routing protocol like OSPF will resolve or banish routing loops, but this needs to occur farther up the support chain. There are other routing problems that, once discovered, should be moved up the chain. Routing problems can manifest themselves in many different ways, including missing IP routes, failure to discover neighboring devices, or failure to connect to neighboring devices once they're discovered. When routing problems are suspected, it is necessary to escalate the issue to the proper technical team. One problem that can be difficult to diagnose is the mismatched maximum transmission unit, or MTU. This is often called an MTU black hole. Different types of WAN connections have different MTU settings. That is, the largest allowable size of a packet that can traverse a link or be accepted by the link. The MTU for Ethernet, by the way, is 1500 bytes. Routers will negotiate the MTU between links using ICMP, that's Internet Control Message Protocol. If ICMP has been disabled on the router, which is a common practice, when a router receives a packet that exceeds the MTU, it will not respond and it will drop the packet. The sending router continues to send the oversized packets into the MTU black hole, never getting a response back that the packets are too big. So the data is flowing, but it's not going anywhere. When suspected, this too should be moved up the support chain to the correct technical team. NIC teaming can also create a problem. This is the process of bonding multiple network interface controllers on a single system for the purpose of increasing bandwidth or for failover purposes. A misconfiguration may actually cause a loss of performance or, in a worst case scenario, the total loss of functionality. If you're dealing with teamed NICs, move it up the support chain. Then there are power failure or power anomalies. Power failures are easy to diagnose but may be difficult to recover from. While battery backups and generators may mitigate the issue, they will not resolve the problem. If the problem occurs within the building, contact the appropriate group responsible for building maintenance. If the problem occurs outside the building, contact the appropriate utility. Electronic devices are sensitive to power issues. Anomalies in the quality of the electricity delivered to the device may cause problems. Using battery backups or uninterruptible power supplies with power conditioners will help to mitigate power anomalies. With problems to escalate covered, let's move on to problems that you can resolve. We will begin with incorrect IP configurations. Under incorrect IP configurations, we will begin with the default gateway. The default gateway is the local network or computer's access to outside networks. An incorrect gateway will keep traffic from reaching its destination. If it's suspected, verify what the correct gateway settings should be and correct it. Then there are duplicate IP addresses. When duplicate IP addresses have been configured, the first device booted up will get the address, and the second one that gets booted up will get an address supplied by a PIPA. This can occur when DHCP address reservations have not been configured correctly. This is easy to verify and correct and should be done when an PIPA address is received by a device. There are other DHCP misconfigurations that can occur. The problem is expressed in a similar manner as the duplicate IP address problem, as in a PIPA address is supplied, and is configured and is caused by a misconfigured DHCP server. Again, verify your DHCP settings and correct. Then there are DNS misconfigurations. Users complain that they cannot get to resources or destinations on the network when using the host name. DNS is used to resolve host names to IP addresses, so a misconfiguration will prevent the function of the DNS process. Verify the correct DNS settings and correct as needed. It's also possible to have incorrect VLAN assignments or incorrect virtual local area network assignments. Users will complain that they cannot get to necessary network resources. This tends to be a single host issue or to involve a small group of hosts. Verify the VLAN settings, and again, correct as necessary. Incorrect interface configurations will also create network issues. Users may complain of poor network performance or not being able to connect to resources at all. This issue tends to affect a whole network segment. Configuration issues could include mismatched port speeds and/or duplex settings on the interfaces. Verify the correct interface configurations and correct the settings. Simultaneous wireless and wired connections will also create some networking issues. Many laptops come with wireless and wired network capabilities built into them. It is possible for a laptop to attempt to use both at the same time. This may cause the device to quit communicating on the network as a whole. Reminding users to turn off wireless capabilities before joining the wired network will resolve this problem. Not having good end-to-end connectivity is another common problem. The complexity of networks will just about guarantee that end-to-end connectivity, the ability to reach remote hosts, will be lost at some point. The ping and tracer utilities can be used to find where the break in communication occurs. This information can then be used to determine the next course of action. Last up is hardware failure. Networking equipment and devices will fail. When this happens, it is usually denoted by the sudden loss or intermittent loss of networking functions or access. The key to resolving this issue is in determining what has failed and replacing it. That concludes this session on troubleshooting common network issues. I began by talking about problems that should be escalated, and then I concluded with problems that should be resolved. On behalf of PACE IT, thank you for watching this session, and I look forward to doing another one. Good day, I'm Brian Farrell, and welcome to PACE IT's session on common network security issues. Today I'm going to be discussing security issues caused by misconfiguration, and then I will conclude on other network security issues. With that, let's go ahead and begin this session. Of course, I'm going to begin by talking about security issues caused by misconfigurations. It's easy to assume that a network is secured from threats, while in reality it may be very vulnerable. A network may actually be vulnerable because of a misconfigured security setting or because of a common practice within an organization. A network may not be as secure as you think due to the ever-changing threat landscape. Nefarious hackers are continually seeking new exploits that they can use to breach network security, including possible misconfigurations in network security settings. These security settings may have been correct at the time that they were set up, but due to the changing landscape, they may be considered a misconfiguration now. A misconfigured firewall and/or access control list may cause a security issue. These can result in 3 different categories of security issues. Traffic that should be blocked isn't, allowing threats in. Traffic that shouldn't be blocked is. This can prevent the receiving of vital updates, or all traffic is blocked. This isn't necessarily a security issue per se, but it is still a misconfiguration. And it is possible for a junior network administrator to just remove the access control list or firewall to allow the traffic to start flowing again, which is a security issue. To protect against a misconfigured firewall or ACL, thoroughly test them before putting them into action. A misconfigured application may become a security threat. A web application that does not perform proper validation of input may lead to a buffer overflow attack. This may lead to a successful attack on the web server on which it is hosted. Thoroughly testing applications before placing them into service will mitigate the threat. Unpatched operating system or firmware will become a major security issue quickly. The manufacturer of operating systems and hardware firmware will often produce security patches or fixes for vulnerabilities as they become known. An unpatched OS or firmware becomes very vulnerable in short order and may become a threat to the network. Most software makers have an updating service. Subscribing to that service will help to mitigate the threat. Open TCP IP ports are a security issue. Open ports on networks are listening for requests for or by services, applications, or protocols. All open ports are a security vulnerability, and there are 65,535 possible ports that may be open. A best practice for network security is to specifically close all unnecessary ports to harden a network. The TACACS Plus and Radius services are often used to authenticate devices and users on networks. A misconfiguration on either may lead to a security issue that allows malicious users to be authenticated to use network resources. Thoroughly reviewing the configuration of authentication services will help to mitigate the problem. In addition, all default local accounts should be disabled. These default local accounts may present a slight opening for a malicious user to exploit authentication services. Active default usernames and passwords are an issue. Almost all devices and applications come with default usernames and passwords to ease the setup process. If left active, these defaults create a security issue, as they tend to be well known or are easy to find through simple research. A best practice is to disable all default usernames and passwords after setting up the device or application. It's time to move on to other network security issues. First up are malicious users. Malicious users may be the single biggest security issue facing any network, and they will fall into one of two categories. There is the untrusted malicious user. This is an outside entity that has exploited a security weakness to gain access to network resources, as in a hacker who has breached a database's security features to gain access to valuable information. Even worse than the untrusted malicious user is a trusted malicious user. This is a person or entity that has been explicitly granted access to network resources that then exploits this trusted position for malicious purposes. And they are harder to guard against because you've already granted them access inside of your defenses. A best practice is to review log files on a regular basis to see what resources are being accessed and by whom to help maintain security. Packet sniffers are also a security issue. Packet sniffers examine network traffic at a very basic level and can be used to help in the administration of a network. But packet sniffers may also be used by malicious users to see what protocols and activities are allowed on the network. This may help them in further attacking the network. Then there is malware. It is usually defined as malicious software that has the intent of causing harm. As a category, malware covers any code-based threat to a network or system. Examples of malware include viruses, trojans, and spyware. To protect against malware, anti-malware applications should be running on every device. To be proactive, end-user education should also be in place to teach them to recognize the dangers that malware presents. The Internet Control Messaging Protocol itself may become a security issue. ICMP can be a valuable tool for diagnosing issues on networks, but it can also become a security vulnerability. ICMP can be exploited in a denial of service type of attack. ICMP can also be used to redirect legitimate users to a new malicious default gateway, possibly resulting in loss of data or sensitive information. It is now a best practice to deny ICMP requests on a router's outward-facing interface. Denial of service or distributed denial of service attacks are becoming more common. In an attempt to bring down a network or website, malicious users will often send thousands or hundreds of thousands of requests for service. The attacker's goal is to make that resource unreachable by legitimate users. Many modern firewalls and other network appliances have been configured to recognize the signature of such an attack and can take steps to mitigate the results. When creating applications, developers often create backdoors into the programs. Backdoors are a method of accessing an application or service while bypassing the normal authentication process. Unfortunately, these backdoors are sometimes left open after the development process has been completed. Once these become known, they can be exploited. In most cases, the application is listening on a specific port for a request for access. The best mitigation technique is to close all unnecessary ports on a network. Kind of sounds familiar, doesn't it? Then there's jamming. All wireless networks use radio frequency channels to transmit data on the network. It is possible to create enough interference on the RF channel that it is no longer usable on the network. An attacker will often use jamming when performing a denial of service type attack. However, it can also be used to perform an evil twin type attack. By jamming the legitimate channel, the attacker is hoping that users will switch to the channel that the rogue access point is transmitting on. Many of the modern networking standards and devices employ techniques to mitigate the threat of jamming, as in both 802.11n and 802.11ac are difficult to jam standards. Then there is banner grabbing. Many network devices display banners when users are signing into or requesting services from network devices. These banners can impart information about the type of device or the type of service that is being requested. This information may be used by a hacker to research possible exploits. The best practice is to disable all unnecessary services and banners on network devices. That concludes this session on common network security issues. I began by talking about security issues caused by misconfiguration, and then I concluded with other network security issues. On behalf of PACE IT, thank you for watching this session, and I hope I get to do another one soon. Good day, I'm Brian Farrell, and welcome to PACE IT's session on common WAN components and issues. Today I'm going to be talking about common wide area network components, and then we're going to move on to common WAN issues. There's a fair amount of ground to cover, not a whole lot of time, so let's go ahead and begin this session. Of course, I'm going to begin by talking about common WAN components. First up are copper line drivers or repeaters. These are used to allow network traffic to go farther distances over copper wire type networks. They take an incoming signal and regenerate it, boosting the strength of that signal, and then they send it back out, thus reducing attenuation. Common to all WANs is the demarc. Demarc stands for the demarcation point. This is the physical point where the telecommunication company's responsibility ends and the customer's begins. The telco takes care of the upstream end of the network, and the customer takes care of the downstream end of the network. The demarc may be simple or it may be very complex, depending upon the size of the organization and the required services. Then there is the Network Interface Unit, or the NIU. In the SOHO environment, the NIU is usually the demarc. Also in the SOHO environment, the NIU is usually provided by the Internet Service Provider, or ISP. An NIU can be a cable modem, a DSL modem, or another piece of hardware that connects the customer to the ISP. One type of NIU is the Smart Jack. It's an NIU that can provide feedback on conditions to the ISP. Smart jacks help the ISP determine if a problem exists on its end of the DMARC through the use of remote loopback capabilities. Many smart jacks can also provide translation between protocols, as in translating a serial PPP communication stream into Ethernet. More than likely on larger networks, you will find CSU DSUs. That's Channel Service Unit, Digital Service Units. This is the interface point that provides the connection between a point-to-point line and the device that is directing network traffic, which is usually a router. The CSU DSU may be an external device, or it may be a removable module inside of a router. Only two CSU DSUs may exist on a single point-to-point line, one at either end of the connection. With the common components covered, let's move on to common wide area network issues. First up is a loss of internet connectivity. Many factors can lead to a loss of connectivity on both sides of the DMARC. Before contacting the WAN provider, check the local area network equipment for its operation. If the issue is not to be found on the LAN side, then contact the wide area network provider. One of the tests that the WAN provider will conduct is a loopback test to check its line for interference. DNS issues are also common in a WAN environment. They may look like a loss of internet connectivity, but it isn't. The users may complain that they cannot connect to an outside source like www.google.com. But it may not actually be a connectivity issue, but a DNS issue. If using a local DNS server, verify the settings and make corrections accordingly. If the network is using the WAN provider's DNS settings, attempt to ping the IP address. If that works, there is a WAN connection. If you then use the ping utility with the fully qualified domain name and this fails, then contact the WAN provider to resolve their DNS issue. Interface issues are also common. Errors on a router's WAN interface can indicate several different issues. Monitoring an interface's status and reading the error reports may provide a clue as to the issue. The most common issue that prevents a good connection is a speed or duplex mismatch. A speed mismatch between interfaces will prevent a link from being established. A duplex mismatch between the interfaces will create errors, as in output and input errors. If you're experiencing discards and drop packets, there's a couple of things to consider. If the device is discarding incoming packets, then more than likely the device's CPU is being overutilized. It may be time to upgrade. If the device is dropping outgoing packets, then there is a bandwidth congestion issue, which may be caused by interference on the line. So either you may be trying to move too much network traffic, or there may be an issue on the wide area network provider's side of the line. Router configurations are a common problem when establishing a new WAN connection. A misconfiguration of the WAN interface of a router will lead to, guess what, a WAN connection issue. If this is suspected, verify the proper configuration settings with the WAN provider. Unfortunately, company policy and practices sometimes get reported as a wide area network issue. Some applications may be throttled or have their available bandwidth reduced for quality of service reasons, leading to slow service, which is a perceived wide area network issue. Also, acceptable use policies may restrict or block access to certain sites or types of sites, which may appear to the end user as a WAN issue. There's not much that you as the technician can do to resolve this, but it is up to you to explain it to the end user. A satellite wide area network connection may also become an issue. If a satellite WAN connection is used, latency will increase due to the distances covered by the transmissions. Latency is the measure of time between the sending of data and the receiving of the data. Careful application of quality of service techniques may mitigate the effects of latency on some applications, but you're still going to have more latency with a satellite connection than other types of connections. Split horizon is another issue. Split horizon is a technique used in routing to help prevent routing loops. With split horizon, a router will not advertise a route to another network out of the interface that it learned the route on. With a point to multi-point wide area network connection, the router may have difficulty with split horizon. It will learn all of the routes available to it on the same interface, but it can't advertise those routes back out of that interface. Creating logical sub-interfaces on the wide area network interface will usually resolve this problem. The logical sub-interfaces appear to the router as individual interfaces, allowing the router to advertise the routes back out of the WAN interface. That concludes this session on common WAN components and issues. I talked about common WAN components, and then I concluded with some common wide area network issues. On behalf of PACE IT, thank you for watching this session, and I hope to do another one soon. Hello, I'm Brian Farrell, and welcome to PACE IT's session on the OSI Networking Reference Model. Today I'm going to begin by talking about a brief history of the reference models, and then I'm going to talk about the network reference models themselves, and then I'm going to conclude with a comparison between OSI and TCP/IP. There's a fair amount of ground to cover, so let's go ahead and begin this session. So let's begin with a brief history. The Open System Interconnection Reference Model is a conceptual model with two major components. The first main component of the OSI Networking Reference Model is an abstract model of networking. It's a 7-layer model. The second major component is a set of specific protocols which allow differing computing systems to communicate with one another despite their different architecture. So why was a networking model required? Well, early networks communicated using proprietary languages. Because of those proprietary languages, early networks could only communicate with like systems. So an IBM network could only communicate with another IBM network. In addition to that, the U.S. government desired a robust computer communication system that could survive disaster. The first networking reference model that was developed was the TCP/IP reference model. The Transmission Control Protocol Internet Protocol reference model was published as the United States Department of Defense standard in 1982. All of the major systems manufacturers adopted the TCP/IP reference model beginning in 1984. AT&T moved the Unix implementation of TCP/IP to open source in 1989, further cementing TCP/IP's place in networking. The OSI reference model came later than the TCP/IP reference model. The OSI model was published in 1983, and it defines the relationships between differing protocols and hardware. It's time to move on to a discussion about the networking reference models in more detail. We're going to begin with the OSI reference model. It is a 7-layer reference model. Layer 1 is also called the physical layer. It standardizes the electrical signals that networks use. It also defines cable standards and how the bits of data are placed on the physical media. Network cables and hubs are part of Layer 1 of the OSI model. Then there's Layer 2, which is also called the data link layer. It's responsible for identifying the individual nodes, both the sending node and the receiving node. It also introduces an error correction method known as the Frame Check Sequence, or FCS. Layer 2 is composed of two sublayers. The first of those is the Logical Link Control layer. It is mainly responsible for flow control and error correction. Then there is the Media Access Control layer. It is mainly responsible for node addressing. Switches and bridges are Layer 2 devices. Then there's Layer 3, the network layer. It's responsible for routing functions between networks. It also identifies networks and nodes on the network. Routers are Layer 3 devices. Then there's Layer 4, the transport layer. It's responsible for breaking the data into smaller pieces for the lower layers and for the actual data transport protocols, two of which are TCP and UDP. The transport layer may be required to confirm the actual delivery of the data stream, and it may be required to offer error correction. And it does this through the use of TCP, or Transmission Control Protocol. Then there's Layer 5, the session layer. This is the layer that is responsible for establishing the initial parameters between two systems. It sets up and tears down the communication channel. Layer 6, or the presentation layer, is responsible for taking data and converting it from a machine-dependent language to a machine-independent language. This is also the layer that has the main responsibility for encryption between networks. And finally, we have Layer 7, the application layer. This is the layer that is responsible for the protocols that request services or functions from other systems. These protocols may not be the actual application. For instance, Internet Explorer is an application that uses HTTP at Layer 7 to request web pages. Now let's talk about the TCP/IP reference model. This is a 4-layer reference model. The lowest layer is the network interface layer, which can also be known as the link layer. It handles electrical signaling, flow control, error detection, and node addressing. Then there's the internet layer. This layer handles routing functions and identifies network systems and nodes on those networks. Then there is the transport layer, which handles breaking the data into more manageable pieces for the lower layers. It is also the layer that is responsible for the delivery method, which can be either reliable or unreliable, and error correction for when reliable delivery is used. And finally, there is the application layer. This layer handles requests for services from applications. It also handles translation to machine-independent languages and encryption. It also sets up and tears down communication sessions between systems. So now let's do a comparison between the OSI and TCP/IP reference models. While TCP/IP is the dominant model, most technicians communicate issues using the OSI model because it is more specific. When a problem occurs, and believe me, they will, it is easier to resolve them with the more highly defined set of specifications of the OSI model versus the specifications of the TCP/IP model. It's easier to resolve an issue at the session layer of the OSI model than it is to track down what went wrong in the application layer of the TCP/IP model. Both the OSI and TCP/IP models are reference models only. It is not mandatory that they be followed. Each developer and manufacturer determines its own method of implementing the reference models. While in theory there will never be a problem in communicating between devices and systems, remember, it is only a theory. Now that concludes this session on the OSI networking reference model. I began with a brief history, then I moved on to the networking reference models themselves, and then I did a very brief OSI and TCP/IP comparison. On behalf of PACE IT, thank you for watching this session. and I hope to do another one soon. Good day, I'm Brian Farrell, and welcome to PACE IT's session on the Transport Layer plus ICMP. Today I'm going to discuss TCP and UDP, and then I'm going to conclude with a brief discussion on ICMP. There's a fair amount of ground to cover, but not a whole lot of time, so let's go ahead and begin this session. Of course, I'm going to begin by talking about TCP and UDP. Before I can talk about TCP and UDP, we need to talk about the transport layer. Most networking models follow the Open Systems Interconnection Reference Model, or the OSI model. It is composed of 7 different layers, which include the application, presentation, session, transport, network, data link, and physical layers. The layers work together to create a system of communication that allows for different types of computing systems or networks to communicate with each other. Layer 4, also known as the transport layer, receives data from the session layer, which is layer 5, and determines what method or type of delivery is required for the data. The transport layer then hands that data with the instructions for the method of delivery to layer 3, which is also known as the network layer, which is then responsible for determining where the data is actually going. There are 2 main transport layer protocols. They are TCP and UDP. TCP, or the Transmission Control Protocol, is a protocol that determines the type of delivery method that will be used in network communications. TCP uses a reliable method to deliver network packets. TCP helps to set up the connection session. It helps to establish error control during the communication session, and it helps to tear down the communication session when it's done. Now, TCP does use a reliable delivery method. One of the main ways that it does this is through the use of a 3-way handshake. The first step of this handshake is the request for the connection. The second step is the reception of the response from the other end. The third part of the 3-way handshake is when the requester sends an acknowledgement back that sets the sequence numbers that will be used with every packet that is delivered. Every packet that gets sent must be acknowledged by the receiver. If the sender doesn't receive the acknowledgement of a packet, the sender will then resend that packet. All packets are sent and received in order. They're never out of order, or they should never be out of order. So now let's talk about UDP, or User Datagram Protocol. It's a protocol that determines the type of delivery method that will be used in network communication, just like TCP. Unlike TCP, UDP uses an unreliable method to deliver network packets. It does not help to set up the connection session. It does not establish error control, and it does not help to tear down the communication session. It uses an unreliable delivery method. This could better be described as a best effort delivery method. It sends the data stream to the destination, trusting that the destination is A, listening for the data stream, and B, willing to accept that data stream. The data stream flows with no acknowledgement of it being received. That's how UDP works. Not all communication can be treated the same. That is why there are both reliable and unreliable delivery methods. With TCP, the sender can be assured that the other end of the line has received all of the packets that were sent and that the packets were received in the proper order. This works well for communication that is not sensitive to latency issues that are associated with the overhead of reliable deliveries. UDP strips off the overhead but sacrifices reliability. It is well suited for network communication in which speed is more important than reliability. When using voice over IP, it is more important for the flow of packets to be continuous than for communication to be held up while waiting for packets to arrive in the right order. Voice over IP communication can survive the occasional dropped packet, but it gets very miserable when it has to wait for those packets to arrive. Now let's move on to ICMP. The Internet Control Message Protocol works at layer 3, which is also known as the network layer, of the OSI reference model, and it is used by IP, or the Internet Protocol, to perform several services. As a messaging service for IP, ICMP packets are carried as encapsulated IP datagrams. It provides information about network issues. The ping utility uses ICMP to test for end-to-end connectivity between two devices using ICMP echo request packets. The traceroute utility uses a combination of ICMP echo requests and destination unreachable packets to map the actual route between two endpoints. Also, if a router's memory buffers are full, it will continue to send out ICMP buffer full messages until the congestion has been reduced. This allows the other routers to slow down their transmissions to avoid packet loss. That concludes this session on the transport layer plus ICMP. I began with a brief discussion on TCP and UDP, and I concluded with another brief discussion on ICMP. On behalf of PACE IT, thank you for watching this session, and I hope you watch another one soon. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Basic Network Concepts Part 1. Today we're going to be talking about encapsulation and modulation. There's a fair amount of ground to cover, so let's go ahead and begin this session. We're going to begin by talking about encapsulation. The Open Systems Interconnection Reference Model, or the OSI model, uses a layered approach to enable disparate devices to be able to communicate effectively. During the communication between two devices or nodes, each layer is only responsible for being understood by the corresponding layer on the other device. As data flows down from the application layer through to the physical layer, it is encapsulated at each layer with information to help the corresponding layer at the other end of the communication line understand what is happening. As the data is received at the other end, it is de-encapsulated or unwrapped as it moves up the OSI stack by the corresponding layer. Let's talk about how encapsulation works. The application layer begins the process by sending data that is encapsulated or wrapped with application layer control information to the presentation layer. The encapsulated data is called a PDU, or Protocol Data Unit. The application layer PDUs are segmented by the presentation layer, with each segment being encapsulated by presentation layer control information. They are now presentation layer PDUs. The process of segmenting and encapsulating continues down through the OSI stack until it is transmitted as bits by the physical layer. The receiving physical layer passes the bits to the receiving data link layer, which reads the data link layer PDU information and then de-encapsulates and desegments it, sending the new packets to the network layer as network layer PDUs. The process of de-encapsulating and desegmenting continues up the OSI stack until it is received by the application layer, where it is finally fully de-encapsulated and fully reassembled. This encapsulation and de-encapsulation allows differing systems to be able to communicate together effectively. With that covered, let's move on to modulation. The physical layer of the OSI stack is responsible for transmitting bits of data across some form of media. So it literally is responsible for transmitting zeros and ones across the media, like a cable. The question arises, how does the physical layer transmit the data across the media? The bits of data are modulated or encoded by the physical layer and placed on the carrier signal of the media, which carries the modulated data onto its next destination. The carrier signal can also be referred to as the carrier channel. Once the bits are received, they are demodulated or unencoded by the receiving physical layer. A carrier signal is a standard waveform, usually in the form of a sine wave, that is used as the base carrier of another input signal. A sine wave is a mathematical curve that is represented by a smooth repeating oscillation. Now let's define modulation. Modulation is the process of varying one or more properties of a carrier signal with an input signal, usually for the purposes of conveying information. Modulation can be used to encode digital network traffic onto media that uses a digital carrier signal, as in using an ISDN connection between two networks. Modulation can also be used to encode a digital signal onto a media that uses an analog carrier signal, as in digital network traffic traveling over the public switched telephone network, or PSTN. Multiplexing is often used with modulation. Multiplexing can be used to increase the number of modulated signals that can be placed onto a carrier signal. So let's talk about multiplexing, and I don't mean your local movie theater. The type of carrier signal will determine if multiplexing can occur. A baseband carrier signal cannot have multiplexing occur, as the modulated signal will consume all of the available frequency or channel width. Multiplexing can be utilized on a broadband carrier channel, as each modulated input is assigned a portion of the channel width of the carrier channel. Multiplexing can use one of two methods to weave streams of modulated signal into the carrier signal. There's frequency division multiplexing. This is the process of mathematically dividing the carrier channel frequency into multiple segments and assigning the results to modulated input signals. Then there is time division multiplexing. This is the process of mathematically dividing the carrier channel width into multiple time segments and assigning the time slots to different modulated signal input streams. It's time to talk about the difference between a baseband and broadband carrier channel. And we're going to begin with baseband. A simple definition of baseband is a stream of data that is sent over a carrier channel as a digital modulated signal. The digital signal will take all of the carrier signal's available frequency or time. While the modulated input does take all of the carrier channel's available frequency, the communication is bidirectional. It can flow back and forth. A simple definition of a broadband carrier channel is a stream of data that is sent over a carrier channel as an analog modulated signal. The analog signal will be assigned a portion of either the carrier channel's available frequency or time. While the modulated input doesn't take all of the carrier channel's available frequency, the communication is not bidirectional. For two-way communication to take place, multiplex channels must be created. That is, a channel for each direction. Now that concludes this session on Basic Network Concepts Part 1. I began with encapsulation and I concluded with modulation. On behalf of PACE IT, thank you for watching this session, and I hope you watch another one soon. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Basic Network Concepts Part 2. Today we're going to be talking about network transmission concepts, and then we're going to conclude with CSMA-CD and CSMA-CA. There's a fair amount of ground to cover, so let's go ahead and begin this session. Of course, I'm going to begin with network transmission concepts. The first concept is wavelength. Wavelength is a measurement of the distance between peaks in a wave pattern emitted by electromagnetic radiation, as in light waves, radio waves, or microwaves. Each type of electromagnetic radiation falls into a specific range of wavelengths. By modifying a wavelength, data can be encoded into the wavelength and transmitted to a receiving device, which then decodes the transmission. Then there's baud rate and bit rate. The baud rate was originally used to measure the speed of a telegraph transmission. It is a measure of the number of state changes in a given period of time. The usual state change that was measured was electricity, as in the number of times the state changed from 0.5 volts to 1.5 volts. The bit rate is a measure of the number of zeros and ones that can be transmitted across a medium in a given period of time. So it is a measure of the actual bits that can be transmitted. It is usually measured in bits per second, or BPS. The bit rate is a more accurate measure of transmission throughput than the baud rate. Then there's sampling size. When converting from an analog audio signal to a digital signal, a computer or other device captures the analog audio waveform and mathematically converts the captured sample into different wavelengths, which is how we get the discrete sounds. This occurs over a specific period of time, which is called the size of the sample, or the sampling size. And finally, there's carrier detect and carrier sense. Carrier detect is when a device can only tell when a carrier signal or channel is present by the reception of a control signal. The presence of the control signal signifies that transmissions can occur. The control signal controls the order of transmissions, so data collisions are not possible. The control signal can also be used to establish the maximum speed of the transmission that can be used. Carrier sense is when a device uses feedback from a receiver to determine if a carrier channel is present. If a carrier signal is detected, the device can send transmissions. Data transmission collisions are possible with carrier sense. And that logically leads us into CSMA-CD and CSMA-CA. The carrier detect method of network transmission works well when there are just a few nodes that need to be connected together. However, as the number of nodes that need to transmit increase, the efficiency of carrier detect begins to decrease to the point where it can become unmanageable. Although the carrier sense method of network transmission is not as efficient when the scale of the network is small, as the number of nodes increases, it becomes more efficient than the carrier detect method. So let's talk about CSMA-CD, or Carrier Sense Multiple Access with Collision Detection. CSMA-CD, of course, uses the carrier sense method of network transmission. Every device on the network uses feedback from a receiver to determine if a carrier channel is present. Every device connected to the network has an equal opportunity to place a transmission on the carrier channel. That's the multiple access part of the name. Before placing a transmission on the carrier channel, a device will listen to the channel to determine if another node is transmitting. If it detects a signal on the carrier channel, the node will wait before attempting to transmit. If no signal is detected, the node is free to send. If two devices send a transmission at the same time, a collision between the transmissions is possible. Sending devices will listen for transmission collisions. If a collision is detected, a jamming signal is sent informing all nodes that a collision has taken place. All devices that receive the jamming signal will wait for a random amount of time before attempting to transmit. Now let's talk about CSMA-CA, or Carrier Sense Multiple Access with Collision Avoidance. CSMA-CA operates in the same manner as CSMA-CD with one exception. It uses a collision avoidance scheme through the use of a controlling device. Before attempting to send data, a device will place a specific signal on the network called a request to send packet, or RTS packet. If no other device is utilizing the network, the controlling device will respond with another specific signal called a clear to send packet, or CTS packet. Once the sending device receives the CTS, it knows it can send a transmission without a collision occurring. CSMA-CD is better suited for high-speed, high-throughput networks and is the specified network transmission standard for the 802.3 Ethernet networking standard, as it has a low amount of network overhead. CSMA-CA is better suited for lower speed, lower throughput types of networks where the possibility of data collision is higher. It is the specified standard for 802.3 wireless networks, or Wi-Fi networks. Now that concludes this session on Basic Network Concepts Part 2. I began with network transmission concepts, and I concluded with a brief discussion on CSMA-CD and CSMA-CA. On behalf of PACE IT, thank you for watching this session, and I hope to do another one soon. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Basic Network Concepts Part 3. Today we're going to be talking about numbering systems, and we will conclude with a very brief discussion on conversion tables. With that, let's go ahead and begin today's session. Of course, I'm going to begin by talking about numbering systems. While computer code and communication can get very complex, it can also be broken down to a basic bit level. A bit has one of two values. It either has a value of 0 or it has a value of 1. These values can be thought of as being either off, which is a 0, or on, a 1. These bit values are actually the only information that computing devices know. By combining and adding different bits together, computers can communicate with each other and programs can be created. Because of this, technicians need to know how to work with binary, or the base 2 numbering system. Binary is a base 2 numbering system where each position has one of two basic values. It is either a 0 or a 1. It is written from right to left with the potential value of digits being doubled with each additional digit that's added. If a 0 is the placeholder, it has a null value or no absolute value. And if a 1 is present, the actual value is double the potential value of the digit to the right. To derive the final value of a binary number, add all of the potential values together, and that will give you the decimal value of the binary number. The binary numbering system is very important when dealing with computers and networking. You should become comfortable with converting from decimal, or base 10 values, to binary, and from binary back to the decimal format. If you need help with that, there are multiple websites that can help. One website that I recommend is mathisfun.com. You can look on their website for their binary numbering lessons. Now let's talk about bit, byte, and nibble. A bit is a single 0 or 1. A byte is 8 bits, and it can also be referred to as an octet. A nibble is half of a byte, or 4 bits. And these terms are used quite frequently when dealing with binary. Now let's talk about hexadecimal. Hexadecimal is a base 16 numbering system that uses the numbers 0 through 9, and then it uses the letters A through F to represent the values 10 through 15. It functions in the same manner as binary, but with base 16. Each hexadecimal digit has a potential binary value of 1111 or 15, and it can be referred to as a nibble as it's half of a byte. A hexadecimal number can often be recognized by the notation prefix of 0 lowercase x, which directly precedes the hexadecimal number. Hexadecimal is widely used in programming and networking, along with binary. Some examples of binary and hexadecimal use include IPv4 addresses, which can be represented by a 32-bit binary number that is divided into 4 8-bit sets. Each 8-bit set is equal to 1 byte and is often called an octet. An IPv6 address, which is a 128-bit binary number, is usually represented by hexadecimal, and it is divided into 8 2-byte sets, each set being separated by colons. And I recommend that you watch my presentations on IPv4 and IPv6 to get a better understanding of how binary and hexadecimal are used in networking. And now let's move on to conversion tables. When working with binary and hexadecimal numbers, I recommend creating a conversion table before doing the math. I find it to be very useful when I need to convert from decimal to binary or from hexadecimal to binary to decimal. Now that concludes this session on Basic Network Concepts Part 3. I began by talking about numbering systems, and I concluded with a very brief discussion on conversion tables. On behalf of PACE IT, thank you for watching this session, and I hope to do another one soon. Hello, I'm Brian Farrell, and welcome to PACE IT's session on the Introduction to Wireless Standards. Today I'm going to talk about CSMA-CA, and then I'm going to conclude with a discussion on wireless standards. There's a fair amount of ground to cover, so let's go ahead and begin this session. Of course, I'm going to begin by talking about CSMA-CA. All wireless Ethernet standards employ an algorithm called Carrier Sense Multiple Access with Collision Avoidance. That's CSMA-CA. A CSMA-CA network involves a method of transmission that avoids packet collisions. Once a node wants to send a packet, it listens to the carrier wave. If no other node is transmitting, it will then transmit. If another node is transmitting, it will wait a random amount of time and then listen to the carrier wave again to see if it's free to send. This differs from a CSMA-CD, which stands for Collision Detection, type of network, which is all about how to transmit after a collision has occurred. Now let's talk about frequency modulation. Frequency modulation is the process used to encode data into a carrier wave. 802.11 uses two main frequency modulation methods. The first one is orthogonal frequency division multiplexing, or OFDM. OFDM is a frequency division multiplexing scheme that uses multiple subcarrier channels to carry data. It is used to mitigate against attenuation, which is loss of signal strength over distance, and multipath issues that exist in networking. The other frequency modulation method is direct sequence spread spectrum, or DSSS. DSSS is a modulation technique that uses spread spectrum technology to effect data transfer. It is used to mitigate the problem of multiple users on a channel and for effective timing between the transmitter and the receiver. Now let's move on to the wireless standards. Wireless networking standards are established by the 802.11 Committee of the Institute of Electrical and Electronics Engineers, or the IEEE. Quite often the term Wi-Fi is used to describe an 802.11 network, which is technically incorrect. Wi-Fi is actually a reference to the Wi-Fi Alliance, which is responsible for certifying that wireless networking equipment actually meets the 802.11 standards. Wi-Fi has become synonymous with the wireless local area network in the English language, so don't be surprised if you find yourself using the term Wi-Fi when you really mean 802.11. Now let's talk about the standards, and first up is 802.11a. It has a maximum speed of 54 megabits per second, and it operates on the 5 gigahertz frequency band. It uses OFDM as its form of modulation and has a maximum distance of 150 feet. 802.11a is compatible with 802.11ac. Then there's 802.11b. It has a maximum speed of 11 megabits per second and it operates on the 2.4 gigahertz frequency band. 11b uses DSSS as its technique for modulation. It has a maximum distance of 300 feet, and it is compatible with 802.11g and 802.11n. Now let's move on to 802.11g. It has a maximum speed of 54 megabits per second, and it also operates on the 2.4 gigahertz frequency band. 11G can use OFDM and DSSS for its modulation techniques. It has a maximum distance of 300 feet. 802.11g is compatible with 802.11b and 802.11n. Now talking about 802.11n, it has a maximum speed of up to 600 megabits per second, and it can operate on both the 2.4 and the 5 gigahertz frequency band. It does use OFDM as its form of modulation. It offers a maximum distance of 300 feet. 802.11n is compatible with 11b, 11g, and 11ac. With the introduction of 802.11n, we now find MIMO, multiple input, multiple output. It's a technology that allows for the increase in speed for the wireless network. With 11n, there can be up to 4 antennas which allow for up to 4 separate spatial streams. And finally, we have 802.11ac. Now 802.11ac offers speed anywhere from up to 433 megabits per second up to multiples of gigabits per second, and it operates on the 5 gigahertz frequency band. It uses OFDM as its method of modulation, but its implementation is an advanced form of OFDM. .11ac offers a theoretical maximum distance of 300 feet. .11ac can be compatible with .11a, g, or n. When 802.11ac was introduced, they improved the MIMO technology, which now allows for up to 8 antennas, which means that there can be up to 8 separate spatial streams of data. Now that concludes this session on the Introduction to Wireless Standards. I began this discussion by talking about CSMA, CA, and then I concluded with a brief discussion on the wireless standards. On behalf of PACE IT, thank you for watching this session, and I hope you watch another one soon. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Introduction to Wired Network Standards. Today I'm going to be discussing the TIA EIA 568A and TIA EIA 568B standards. Then I'm going to move on to Ethernet standards, and I'm going to conclude with some other standards. I have a whole lot of information to cover, but not a whole lot of time, so let's dive into today's session. Of course, I'm going to begin with the TIA EIA 568A and 568B wired standards. The TIA EIA 568A and 568B standards deal with twisted pair wires. These are the two cable pinout standards that are regulated by the TIA EIA. That's the Telecommunications Industry Association Electronic Industries Alliance. The pinout standards specify the ordering of the wires to ensure that proper networking communication can take place. The T568A standard is white, green, green, white, orange, blue, white, blue, orange, white, brown, brown. On the other hand, the T568B standard is white, orange, orange, white, green, blue, white, blue, green, white, brown, brown. All modern Ethernet networks that utilize unshielded twisted pair, UTP, or shielded twisted pair, STP, should use the TIA-EIA standards. As a quick refresher for twisted pair wiring, here are some common tools that you will need. There are wire strippers. These are used to remove the insulating jacket from the cable. Then there are crimping tools. These are used to secure the wires into modular connectors. Then there are punch-down tools. These are used to secure wires into punch-down blocks. And finally, there are cable testers. These are used to test the integrity of the network cables that you've just created. With that covered, let's move on to Ethernet standards. First up are distance limitations. Twisted pair copper wire is limited to 100 meters without a repeater unless otherwise stated. Coaxial LAN cabling is limited to either 185 or 500 meters depending upon the coaxial cable that is used. As an example, a 10-base-2 coaxial network uses RG58 and is limited to 185 meters in length. On the other hand, a 10-base-5 coaxial network using RG8 is limited to 500 meters. With fiber optics, LAN transmission is limited by the cable type that is used. The current maximum is over 40 kilometers over a single-mode optical fiber, or SMF fiber. Now let's talk about twisted pair cable standards. There's 10-base-T, that's 10 megabits per second, using UTP over a minimum of Cat3 cable. Then there's 100-base-T, that's 100 megabits per second, using a minimum of Cat5. You can also have 100-base-TX. This is 100 megabits per second networking using 2 pair over a minimum of Cat5. Then there's 1000-base-TX. This is 1 gigabits per second networking using 2 pair over a minimum of Cat5e cable. Then there's 10G-base-T, that is 10 gigabits per second networking using a minimum of Cat6, but it's only good for 40 meters. Finally, there's also 10G-base-T, that's 10 gigabits per second networking using a minimum of Cat6a cabling, but that's good for up to 100 meters. Now let's move on to the multi-cable standard, and that's 1000-base-X. Under this standard, there's 1000-base-SX, which is 1 gigabit per second networking over a short distance multi-mode fiber, and it's usually less than 2 kilometers. Then there's 1000-base-LX. This is 1 gigabits per second networking over long distance single mode fiber, and it's usually a greater span than 2 kilometers. And finally, there's 1000-CX. This is 1 gigabits per second networking over a coaxial cable that can be up to 25 meters long. Now let's talk about 10 gigabit networking. First up, there's 10G-base-SR over multi-mode fiber, and it's good for up to 300 meters. Then there's 10G-base-LR over single-mode fiber, which is good for up to 10 kilometers. Then we have 10G-base-ER, which is over single-mode fiber, and it's good for up to 40 kilometers. Then we have 10G-base-SW. This runs over MMF, and it's good for up to 300 meters, and it's used on a wide area network. Then there's 10G-base-LW, which runs over SMF up to 10 kilometers, and it's also used in a wide area network. And then there's 10G-base-EW, which runs over single mode fiber for up to 40 kilometers, and again on that SONET type WAN network. Then there's 10G-base-LX4, which runs over single mode fiber, and it's good for up to 300 meters. Then there is 10G base LX4 over multi-mode, which is over multi-mode fiber, which is good for up to 10 kilometers. And finally, there is 10G base CX4. This runs over InfiniBand copper cabling, and it's good for up to 15 meters. It's time to conclude with some other standards. First up is DOCSIS, or Data Over Cable Services Interface Specification. These are the standards that have been established to provide the interface requirements for data transmissions over a broadband cable network. To achieve the best performance when using broadband cable, the cable modem should meet the highest DOCSIS standard used by the cable provider. The most current DOCSIS standard is 3.1, which allows for up to a theoretical maximum download speed of 10 gigabits per second with a theoretical upload speed of 1 gigabit per second. Then there's the IEEE 1905.1-2013 standard. This is a standard that defines a network enabler or device that is used to create a convergent home networking environment that includes different types of wired and wireless networks. The standard also includes Ethernet over power line, which is using the existing electrical wiring in a structure as the media to transport data. The standard also includes Ethernet over HDMI, which is using an HDMI interface and cable to transport network traffic. Now that concludes this session on the Introduction to Wired Network Standards. I began by talking about the TIA EIA 568A and 568B standards. Then I moved on to the Ethernet standards, and I concluded with a brief discussion on some other standards. On behalf of PACE IT, thank you for watching this session, and I hope to do another one soon. Good day, I'm Brian Farrell, and welcome to PACE IT's session on security policies and other documents. Today I'm going to be discussing some security policies, and then I will conclude with a brief discussion on other documents. There's a fair amount of ground to cover, but not a whole lot of time, so let's go ahead and begin this session. Of course, I'm going to begin by discussing security policies. Policies are a set of guidelines established by management that are used to set the expected behavior in the workplace. Procedures are different than policies in that a procedure is a set of steps required to be taken in a given situation. Policies and procedures work hand in hand to create a safe and secure work environment in which employees know the guidelines and what is expected of them. Policies and procedures should be given to every person on the day they start, and periodic training should be conducted to ensure that they remain fresh in everyone's mind. One of the security policies to consider is the consent to monitoring. This is a policy that establishes an employer's right to monitor the employee's actions and communications. This can include monitoring emails. If they traverse company equipment in any way, then the emails are not considered private, but are actually company assets that they have a right to view and do with as they please. These consent to monitoring policies also include the monitoring or recording of phone conversations, also monitoring activities on computers, hard drives, and phones. In a highly secure work environment, it may also include the video monitoring and recording of normal work activities. Another security policy is a clean desk policy. This is a policy that is concerned about the handling of sensitive data. Sensitive data should not be left unattended in a workplace and should be put away when not in use, not left on a desktop. These policies also include the computer desktop. Sensitive data should not be left easily accessible on the PC. Then there are recording policies. This is a policy that restricts the use of cameras, tape recorders, portable storage devices, or any other device that may be used to record or copy sensitive workplace information. Then there are equipment access policies. They're a security policy that establishes who has access to which equipment and when. These could include access to server rooms, wiring closets, network racks, or any other area that is deemed to have a security risk. There are security policies that deal with the handling of user or customer information. They're used to establish how to secure sensitive employee and customer information. User and customer information is a major target of hackers when they breach computing systems. The loss of control of this data can severely damage a company. Any policy that is used to help secure the workplace or company data is, by default, a security policy. Approximately 80% of all network and data breaches occur from within the companies that are attempting to secure the data. Sometimes they occur by mistake. However, all too often they are intentional. All policies should have an enforcement aspect to them that details what employees should expect to happen if they violate the policy. The range of actions can be from retraining to termination and prosecution. Now let's conclude with a brief discussion on some other documents. First up is the AUP, or Acceptable Use Policy. These are a set of rules and guidelines established by the creator, owner, or administrator of information systems that detail what users may or may not do with that information system. It is considered to be part of the security policy. The AUP should be fairly detailed in what is allowed or not allowed to occur. All users should be required to sign the acceptable use policy, and these records should be kept on file. Then there are network policy documents. There are a broad range of policies that establish the guidelines for the network. They include policies that control the use and operation of the network, as well as policies on how to implement changes to it. Many security policies fall under the general network policies category. There are some standard business documents that you should be familiar with. The first one is the Memorandum of Understanding, or MOU. It's an agreement between two or more organizations that detail how those organizations are to undertake a common course of action. An MOU is often used before a legally binding agreement has been created. Sometimes the MOU is called a Letter of Intent, or LOI. Then there is the Statement of Work, or the SOW. It's a detailed document that specifies what work is to be performed, the expected outcome of the work or the deliverables of the work, and the timelines to perform that work. The SOW plays an important role in project management documentation. Then there is the Master License Agreement, or the MLA. It's a legal agreement between two entities in which one agrees to pay the other for the use of a specific piece of software or a software package for a specific period of time. So the person using the software doesn't actually own the software. The creator or the vendor retains the legal rights to that software or that software package. And finally, there's the Service Level Agreement, or the SLA. It's an agreement that details the allowable amount of response time the vendor has to resolve an issue or problem. The SLA is most commonly associated with a service contract. Now that concludes this session on security policies and other documents. I briefly talked about security policies, and then I concluded with a discussion on some other documents. On behalf of PACE IT, thank you for watching this session, and I hope to do another one soon. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Introduction to Safety Practices, Part 1. Today I'm going to be talking about electrical safety, and then I'm going to move on to installation safety. I have a fair amount of ground to cover, but not a whole lot of time, so let's go ahead and begin this session. Of course, I'm going to begin with electrical safety. Electrical grounding is used to protect technicians and equipment in the case of electrical installation failure. Electrical grounding provides an alternate path for the electricity. This is often referred to as a return to earth. All electrical systems should be connected to properly grounded circuits. This helps to protect both the technician and the equipment. Then there's ESD, or electrostatic discharge. ESD is caused when two electrically charged objects that have different amounts of electrical charge come into contact, creating a sudden flow of energy between the objects as they normalize the levels. This is a static discharge. ESD can damage sensitive components, particularly the CPU and/or your random access memory. Using an ESD mat helps to reduce the chances of ESD. Using an ESD strap will further reduce the chances for ESD. The strap goes around the wrist of the technician and then is clipped to a ground source, usually to an exposed metal surface inside of a piece of equipment's case. You should always practice self-grounding. Self-grounding is a normalization technique used to equalize the amount of electrical charge between the worker and the equipment being worked on. After the case has been opened and the ESD strap is attached to a ground source, touch an exposed metal surface inside the case before actually touching any of the components. This will normalize the electrical charge between you and the equipment that you're working on. In some cases, additional equipment grounding may be necessary. In case of an electrical fire, unplug the power source or turn off the circuit breaker. Always use a Class C or multi-class fire extinguisher on electrical fires. Never use water. You run the risk of electrocution and damaging that equipment even more than the fire is already doing. So let's talk about fire suppression systems. Building codes often call for the installation of fire suppression systems, and there are several different types of common systems. There's the wet pipe. The overhead pipes are pressurized and contain water all of the time. Then there's the dry pipe. The pipes are not pressurized. The water is contained in a holding tank until a fire breaks out, and then it is pumped to the area where it needs to be dispersed. There are pre-action types of fire suppression systems. They're similar to a dry pipe system, but the sprinkler head contains a thermal fusible link that must melt before the water is released. Then there's the deluge fire suppression system. These are designed to release a large amount of water in a short amount of time into a predefined space. The deluge system is the least desirable option for electrical components. On the other hand, a halon type system is the most desirable type of fire suppression system for electrical components. Halon is a non-conducting, volatile gaseous chemical. It works by chemically disrupting the combustion process. Halon does not leave a residue upon evaporation, and unlike water, halon will not ruin electrical components. It is safe for exposure to humans in limited amounts for a limited amount of time. Halon is also environmentally safe. It's also known as a clean agent. Now it's time to move on to installation safety. First up is using proper lifting techniques. Bend at the knees, not at the waist. Keep your head up when lifting. Avoid twisting when carrying items. If the item is heavy or awkward, request help in lifting it. Also remember, most companies establish weight limitations. So if you're going to lift something that is going to exceed that weight limitation, ask for help. More than likely, you are going to need to install equipment racks at some point in time or another. Racks are used to help create a clean, organized environment, especially when they're used with proper cable management techniques. Racks are designed to provide sufficient airflow for the electrical components that are placed in them. When assembling and installing racks, always follow the manufacturer's instructions. Always use the proper tools to prevent damaging the racks or the fasteners that hold them together. Many servers and networking components come rack ready. That means they're specifically designed to be placed into an equipment rack. Let's talk about rack placement. When designing a room that is going to hold multiple racks of computing systems, some thought needs to go into the placement of those racks. HVAC and rack placement should be done concurrently. Heating, ventilation, and air conditioning systems should be designed to control both heat and humidity levels. When multiple racks are going to be installed, creating a hot aisle, cold aisle design is recommended. The hot aisle is the side of the aisle that receives the exhaust airflow from the computing equipment. This aisle should face an HVAC air intake. The cold aisle is the side or aisle that the air intakes of the computing equipment face. This aisle should face an HVAC air vent. Also, whenever possible, a server room should be designed with a raised floor to help protect against water damage. The raised floor, like a drop ceiling, can also be utilized as part of the cable management system. Let's talk about tool safety. Always use the proper tool for the job. That is what it was designed for. Do not use pencils as a probe. It is possible for the pencil to conduct electricity, leading to an ESD situation or shock hazard. Do not use magnetized tools when working on electrical components, as the magnetic charge can be harmful to the magnetically kept data, and that magnetically charged tool may damage sensitive components. When using compressed air to blow out debris, maintain a minimum distance of 4 inches from the nozzle to the component. Always use isopropyl alcohol to clean products in place of rubbing alcohol. Rubbing alcohol contains a higher water content of approximately around 30%, whereas the water content in isopropyl alcohol is lower. Never use a standard vacuum cleaner when vacuuming electrical components is necessary. Due to the design of the standard vacuum, electrostatic discharges are a common occurrence. There are specifically designed vacuum cleaners that can be used on electrical components. Now that concludes this session on the Introduction to Safety Practices Part 1. I talked about electrical safety, and then I concluded with installation safety. On behalf of PACE IT, thank you for watching this session, and I hope to do another one soon. Good day, I'm Brian Farrell, and welcome to PACE IT's session on the Introduction to Safety Practices Part 2. Today I'm going to talk about the MSDS, and then I'm going to conclude with some emergency preparations. There's a fair amount of ground to cover, so let's go ahead and begin this session. Of course, I'm going to begin with the MSDS. Part of any safety-first approach to a safe work environment includes knowing what hazards are present in the workplace. Material Safety Data Sheets, or MSDSs, contain safety information on materials and chemicals found in the workplace. An MSDS will contain all known health issues associated with a particular material. It also outlines what protective measures must be taken to reduce risks from exposure and what actions must be taken if the chemical is ingested. The MSDS will also detail the physical properties of the material, as in its flash point or boiling point. And the MSDS will outline the proper steps to take when disposing of it. Each workplace will have its own set of MSDSs, as each workplace is different. It is your responsibility to understand the hazards that are present, so you need to know where the MSDSs are kept for your workplace. It's time to move on to some emergency preparations. Part of any safety-first approach to a safe work environment includes preparing for various types of emergencies. These preparations should be detailed in a set of emergency procedure documents. The procedures should contain escape routes, including where employees will meet to ensure that all are accounted for, information on what type or types of fire suppression systems are present, as well as what steps have been taken to increase the day-to-day safety in the workplace. There are some building layout considerations that concern emergency preparations. All walls should have a minimum 2-hour fire rating. This is the amount of time it takes for the average fire to burn through the wall. Exterior doors and other secure doors must be designed to resist forcible entry, but the doorways should also be designed to be able to handle the amount of expected traffic in an emergency. Fire suppression systems should be appropriate for the type of asset that they are protecting. A wet pipe system is not appropriate for a server room or data center. However, a halon system may not be the correct fire suppression system for an open cubicle area. Backup power should also be incorporated into the building layout. Not all areas are going to require backup power, but for some areas it is going to be essential. Emergency preparations need to include escape plans. Each area or room should have an escape plan map posted in a prominent area, ideally by the main access doorway into that area. This map needs to show the preferred route out of the facility. The map should also include the meeting area outside of the danger zone. This allows for supervisors or managers to account for all personnel. Safety or emergency exits should be clearly marked. They should also be well lit with independent battery power sources. They should be wide enough to handle the expected traffic, and emergency exits should always be kept clear of obstructions. Talking about doors, there are some other considerations. Are they going to be fail open or fail close? So what happens to doors with electronic locks when the power is out needs to be considered. They could be fail close type doors. With this type of door, when the power is cut, the locks engage. These are suitable for keeping secure areas secure in an emergency. Then there are fail open type electronic locks. When the power is cut, the locks disengage. These are suitable for non-secure areas or for areas where two-way traffic is going to occur in an emergency. In many facilities, fail-close type fire doors are used. Usually they're kept open by electromagnetics. Once the fire alarm has been tripped, the power is cut to the magnets and the doors swing closed. They usually do not lock when closed, but are used to help slow the spread of fire or other dangers. Another emergency preparation that should be considered are emergency alert systems. All facilities should have an emergency alert system installed. It is usually required by local building codes. These are your fire alarms and whatnot. Combinations of sound and light have proven to be highly effective. In some situations, it may be advisable to connect the facility to the National Emergency Alert System. Now that concludes this session on Introduction to Safety Practices Part 2. I began with the MSDS and then I concluded with emergency preparations. On behalf of PACE IT, thank you for watching this session, and I hope to do another one soon. Good day, I'm Brian Farrell, and welcome to PACE IT's session on rack and power management. Today I'm going to talk about rack management, and then I'm going to conclude with a brief segment on power management. With that, let's go ahead and begin today's session. I'm going to begin by talking about rack management. Rack systems are specially designed racks used to hold networking and computing equipment. Sometimes they are referred to as server racks. These rack systems follow one of several different designs. However, they all follow the same height specification. That specification is the standard unit, and it's designated by the capital letter U. Now, the standard unit involves the amount of vertical space that can be used to hold equipment. A standard unit is equal to 1.75 inches. So a 15U rack has 26¼ inches of vertical storage space. Most rack servers and enterprise-level networking equipment are designed to fit within rack systems. There are several different types of racks. Racks are normally either 2-post or 4-post racks. They may be freestanding or they may be floor-mounted. Server rail racks have slide mounts to make it easy to pull out servers to perform necessary maintenance. Now let's talk about device placement. Devices that generate the most amount of heat or are not heat sensitive should be placed towards the top of the rack. Devices that generate the least amount of heat or are heat sensitive should be placed toward the bottom of the rack. All equipment cold air intakes should face the same direction. All equipment exhaust outlets should therefore also face the same direction. When mounting equipment in racks, vertical space should be left between the equipment to promote adequate airflow. When multiple rows of racks are implemented, a hot aisle cold aisle approach should be used to promote proper airflow and cooling. Racks should be monitored for environmental factors to help ensure the health of the servers and other equipment. Monitors should be in place for temperature, humidity, vibration, water leaks, smoke, and intrusion. And that brings us to rack security. Most rack systems do not come with rack security in mind, but it can be easily added after rack installation. Rack doors can be added that have either keyed or electronic locks. If the equipment is not secured, it can be easily stolen. Now let's have a brief discussion on power management. So before I begin talking about power management, let me give you a little bit of trivia. We're all familiar with the power symbol that you see there to the right. That's actually a binary symbol. What that is a 0 with a 1 poking through it. I know, not very relevant to today's discussion, but it's an interesting bit of trivia. Now, power is often overlooked when designing a network. However, without power management, the network may never work properly. Most people assume that when they plug a piece of equipment into a wall socket, that piece of equipment is going to power up just fine. In most cases, they are correct. However, if the circuit cannot provide enough amps to the equipment, damage may occur. It is important to know the power requirements and loads for all of the equipment that will be in place. This helps to ensure that the proper electrical circuits are installed so that sufficient power is delivered where it is needed, when it is needed. Power converters convert electrical energy from one form to another, as in from AC to DC, or from one voltage level to another. On the other hand, power inverters are a type of power converter that specifically converts voltages from DC to AC. Then we have the uninterruptible power supply, the UPS. It uses power converters to receive electrical current from an AC electrical source, and it passes that current to a battery or set of batteries for storage. It then uses a power inverter to receive DC current from the batteries and pass it to another device as a conditioned and well-regulated AC flow. They're used to provide a steady stream of conditioned electrical power to components. They help to protect sensitive electrical components from power anomalies, either from power spikes, power outs, or from power sags. In some cases, you may want to consider installing power redundancies. Critical components should include redundant power supplies. That means that if one power supply fails, the other one takes over immediately without any loss of service. Now that concludes this session on rack and power management. I began by talking briefly about rack management, and then I concluded with a brief discussion on power management. On behalf of PACE IT, thank you for watching this session, and I hope you watch another one soon. Good day, I'm Brian Farrell, and welcome to PACE IT's session on cable management. Today I'm going to be talking about cable distribution, and then I will conclude with some cable management components. We have a fair amount of ground to cover with not a whole lot of time, so let's go ahead and begin this session. Of course, I'm going to begin by talking about cable distribution. And the first item under cable distribution is the main distribution frame, or MDF. This is the location where the DMARC extension, main switch or router, and patch panel are placed. The MDF is where outside traffic enters a location and is then distributed to the internal network. It is possible to also have an intermediate distribution frame, or IDF. It's a location's solution for when a single MDF is not sufficient. They usually occur in multi-story buildings. The IDFs are connected to the MDF by vertical cross-connect cables, or VCC cables. It is common for an MDF to contain separate IDF panels for each floor of a building. A vertical cross-connect is the main patch panel for a location. It usually resides in the same location or very close to the DMARC and main switch or router. I mentioned patch panels earlier, so let's talk about those. They're used to terminate network cable runs, usually within a building, as in from the wall jacks to a central location. The network runs are called horizontal cabling. Patch panels are used to organize and administer the physical aspects of the network cables. Network runs are punched down to the back of the patch panel, which normally contains either a 66 or a 110 block, with an associated port on the front of the patch panel. Patch cables are used to connect the patch panel ports to networking gear, quite often a switch. Workstations connect to the patch panel using horizontal cabling. This location is called the Horizontal Cross Connect, or HCC, and is usually located in the IDF. Switches may or may not be present in this location. If a workstation needs to be relocated to a different switch or port, all that needs to be done is to make the change in the location of the patch panel. So you unplug the cable from one port and you plug it into a new port. With that covered, let's talk about cable management components. Labeling is an important part of cable management. It can cause stress when working with networks, but it doesn't have to. The key to proper labeling is to create a naming convention, which is a systematic and consistent method that makes sense for the situation. Proper labeling will ease the management of the physical aspects of the network, especially when dealing with cables. Labels should be placed on everything that deals with the network, beginning from the wall jacks all the way through to the patch panel, switches, and routers. The naming convention should be documented and kept with the network diagrams. Let me give you an example of a naming convention. Suppose Office 219 has network outlets on all four walls. The jacks could be labeled 219N, 219W, etc. And that would be for 219 North or 219 West, etc. The horizontal cabling from 219 feeds into a patch panel in an IDF located on the second floor that contains two 48-port switches that tie in all the horizontal cross connects. The cables coming in from Office 219 to the patch panel could be labeled 219W or 219S, etc., as it relates to their location in the office. The switches could be labeled SW2A and SW2B. Now suppose that the patch cables for Office 219 connect to switch 2B's ports 20 through 24. The patch cables could be labeled 219N-SW2B-21 or 219E-SW2B-22, etc. The key is to be consistent and to document everything. And finally, there are cable trays. Masses of cables can block airflow and act as an insulator that allows for excessive heat to build up. Cable trays are used to organize cabling and to keep it away from areas where cabling may cause heat to build up. Cable trays keep bundles of cables neat and fairly well organized. That concludes this session on cable management. I talked about cable distribution and then I briefly covered some cable management components. On behalf of PACE IT, thank you for watching this session, and I hope to do another one soon. Good day, I'm Brian Farrell, and welcome to PACE IT's session on the basics of change management. Today we're going to be talking about the reasons for change management, and then we're going to conclude with some different change management processes. I have a fair amount of ground to cover, but not a whole lot of time, so let's go ahead and begin this session. Of course, I'm going to begin with the reason for change management. In a fairly simple network, it is fairly easy to evaluate not only the necessity for a change, but also the possible impacts of that change. However, as the network system increases in size and complexity, it becomes more difficult to not only determine what changes are necessary, but also the possible impacts that the proposed changes will have on the system as a whole. It is quite possible, even highly probable, that a single change will have a ripple effect on the whole system. Change management processes are used to introduce changes to a system in a controlled manner to minimize possible disruption and potential pandemonium. With the reason for change management covered, let's move on to different change management processes. First up is document the reason for a change. Proposed changes should have a solid reason for occurring. A best practice is to include why the change is needed for IT reasons and also for business reasons. As the change proceeds through the process, more documentation may be added to the reason for a change. So let's talk about the change request. A formal change request procedure is used during the approval process and should include several other subdocuments that can be used to gain approval. One of those documents is the configuration procedures documents. These document the exact steps required to implement the change, including affected devices, applications, and processes. The change request should also include a rollback process. As all change carries risk, a plan to reverse changes is required in order to gain approval. Then there are potential impact documents. The potential impact documents are a good faith effort to identify all possible impacts to the overall system, both the positive and the negative. Then there is the notification procedures. After the potential impacts have been identified, the people responsible for the affected systems must receive notification of the proposed change. Keeping your stakeholders informed and involved will greatly increase the chances of a successful change. Let's talk about approval processes. Proposed changes should be vetted and approved, not only by management, but also by senior IT personnel, security experts, and by a selection of those affected by the change. Some companies create change control boards to not only evaluate proposed changes, but to also implement a means of approving changes. These boards also assure that all approved changes have been fully tested and documented. The change boards meet periodically to assess the status of an approved change. This helps to keep it on track for implementation. Change boards maintain responsibility for the change and verify that the process is proceeding according to the configuration procedure. And finally, change boards help to ensure that approved changes are implemented correctly. When planning out a change to an IT system, it's important to involve a maintenance window procedure. A maintenance window is the amount of time that a system will be down or unavailable during the proposed change. Before the final schedule is developed, an evaluation of all affected systems must be performed with particular attention paid to mission-critical systems. It is possible that the proposed maintenance window may exceed the allowable downtime for critical systems, which will affect when the maintenance window can be scheduled. A sub-procedure to the maintenance window procedure is authorized downtime. Once a maintenance window has been identified, it is then possible to determine the optimum time to implement the change. In many cases, system changes need to occur during off hours, as in after the close of business or during weekends when systems are not utilized as much. Then there's the notification of change procedure. After sufficient time has elapsed in which to evaluate any issues, all stakeholders, those are the people who approved the change and all others affected by the change, should be notified of the successful completion of the change. This allows the stakeholders to further monitor the systems for any unforeseen or residual issues relating to the change. And finally, there's final documentation. The change process should end with an update to the appropriate documentation, including network configurations, additions to the network, and physical location changes. A closing change report should also be created that summarizes the change to help refine the change procedures and processes even further. This closing report should include what went right and what went wrong during the approved change. That concludes this session on the basics of change management. I talked about the reasons for change management, and then I concluded with different change management processes. On behalf of PACE IT, thank you for watching this session, and I hope to do another one soon. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Common Networking Protocols, Part 1. Today I'm going to briefly discuss TCP and UDP, and then I'm going to briefly run through some common ports and protocols. With that, let's go ahead and begin this session. Let's begin with a brief overview of TCP and UDP. Both Transmission Control Protocol and User Datagram Protocol are both transport layer or layer 4 protocols. They're both responsible for the delivery of network data between nodes. While they are both layer 4 protocols, they do have some differences. TCP uses a reliable delivery method. This ensures that all the packets that are sent are received. It uses acknowledgments as a means of error correction. TCP also establishes flow control to reduce the error rate and ensure proper delivery. On the other hand, UDP uses a best effort delivery method. It sends data but doesn't care if the packets are all received. There is no error correction, and with UDP, speed and low network overhead are the major concerns, not the reliable delivery of the information. Now let's discuss some common ports and protocols. First up is HTTP, that's Hypertext Transfer Protocol. It's the primary protocol used to transfer data over the internet. It is assigned to port 80. Then there's HTTPS, which is Hypertext Transfer Protocol Secure. It is the primary protocol to securely transfer data over the internet using SSL or TLS technology. That's Secure Socket Layer or Transport Layer Security technology. In actuality, SSL should no longer be used. You should only be using TLS. By default, HTTPS is assigned to port 443. Then there's NetBIOS. That's Network Basic Input Output System. This was originally developed to allow hosts to be able to communicate with servers. By default, it's assigned to ports 137 through 139. Then we have SMTP, or Simple Mail Transfer Protocol. This is the protocol that's used to transfer email from a client to an email server or to transfer email between different email servers. By default, it's assigned to port 25. Post Office Protocol version 3, or POP3, is the protocol used by clients to retrieve email from servers. Once engaged, POP3 downloads all the messages from the servers. The user cannot access email messages until they have been downloaded by the POP3 protocol. POP3 is assigned to port 110. In contrast to POP3 is IMAP. That's Internet Message Access Protocol. It's a protocol used by clients to access email on email servers. Allows the client to administer and organize email on the server into folders without having to download it first. By default, IMAP is assigned to port 143. Next up is SIP, or Session Initiation Protocol. It's a protocol that is most commonly used to set up and tear down multimedia communication sessions, as in Voice over IP. In a Voice over IP session, SIP is used to establish and to terminate the session. Session Initiation Protocol is commonly assigned to either port 560 or to port 561. Often used in conjunction with Session Initiation Protocol is RTP. That's Real-Time Transport Protocol. This is the protocol that is commonly used to format and deliver multimedia or streaming content. As an example, RTP handles the flow of packets in a Voice over IP session after Session Initiation Protocol has established the connection. RTP is commonly assigned to ports 5004 and to port 5005. Then there's Media Gateway Control Protocol, or MGCP. It's a protocol that defines a means of communication between a packet-switched network and a circuit-switched network, as in the PSTN. It can be used to set up and maintain and terminate calls between multiple endpoints, as in teleconferencing. It's commonly assigned to ports 2427 and or to port 2727. Last up, we have H323. This is a protocol that provides a standard for delivering video over IP networks. It defines how real-time audio, video, and data are to be transmitted. It provides signaling and bandwidth control. It's commonly assigned to port 1720. That concludes this session on Common Networking Protocols, Part 1. I did a brief summary of TCP and UDP, and then I briefly ran through some common ports and protocols. On behalf of PACE IT, thank you for watching this session, and I hope you watch another one soon. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Common Networking Protocols, Part 2. Today I'm going to be talking about the difference between ports and protocols, and then I'm going to conclude with a brief discussion on some common ports and protocols. With that, let's go ahead and jump into this session. Of course, I'm going to begin by talking about the difference between ports and protocols. Ports are a method of specifying what protocol or service to access. Many protocols and services use default ports so they are easy to locate. There are 65,536 ports available to be used for communication, but port 0 is reserved. The first 1,024 ports are specifically assigned and are called well-known ports. If you would like to learn more about those, you can check out the iana.org website. Ports can be thought of as a phone number extension. The IP address is the main number you are trying to reach. The port is the extension for the service or protocol that you want to access. Protocols can be thought of as the language that two applications on either side of the connection agree to speak. Protocols translate requests into services. Most protocols use predefined ports, but some protocols must be user configured for the ports that they use. Something to remember, ports are not protocols and protocols are not ports. Even though the two are closely associated, they are not the same. Ports are used to request or access services or applications. Protocols are the services or applications that are being requested. When a requester seeks to connect to a specific port, the requester is dynamically assigned a port number to listen to for the response. This also allows computers to have many concurrent connections at the same time. It's time to move on to a brief discussion on common ports and protocols. First up is the File Transfer Protocol, or FTP. It's a standard protocol for transferring files between computing systems, and it does require user authentication. FTP uses ports 20 and 21, although nowadays it mostly just uses port 20. Then there's TFTP, or Trivial File Transfer Protocol. This is used to transfer files between servers and clients, but no user authentication is required. By default, TFTP is assigned to port 69. Then there's SNMP, or Simple Network Management Protocol. It's a protocol used to monitor and manage local area networks. By default, it is assigned to port 161. Then we have Telnet, which is a protocol that is used for remote access to systems. It is unsecure, but it is also a bidirectional terminal service that comes in handy on occasion. By default, Telnet uses port 23. More secure than Telnet is SSH, or Secure Shell. It's a protocol that's used to encrypt data traffic on networks. It can be used in place of Telnet to provide a secure bidirectional terminal connection. By default, SSH uses port 22. A very useful protocol to have is DNS, or the Domain Name System Protocol. This is the protocol that's used to map computer names to their IP addresses. DNS is assigned to port 53 by default. Then there's DHCP, or Dynamic Host Configuration Protocol. This is the protocol used within networks to automatically configure computers with the correct IP configuration. There are two ports used with DHCP. Requests are assigned to port 67. Responses from the DHCP server are assigned to port 68. Remote Desktop Protocol, or RDP, is used in Microsoft networks by both the Remote Desktop Connection and Remote Assistance applications to make remote connections. RDP is assigned to port 3389. Last up, we have SMB, or Server Message Block. It's a protocol used to transfer files over a network. The process is transparent to the user. The user never sees SMB. SMB can be configured to run over NetBIOS on ports 137 through port 139. But by default, SMB is assigned to port 445. That concludes this session on Common Networking Protocols Part 2. Today I talked about the differences between ports and protocols, and then I briefly discussed some common ports and protocols. On behalf of PACE IT, thank you for watching this session, and I hope to do another one soon.